Hey everyone, welcome to the Drive Podcast. I'm your host, Peter Attia. Hey Matt, awesome to have you back on the show. It's been a while because you were one of the very, very initial and original guests on this podcast. So I've been looking forward to having you back from almost the moment we finished our first discussion.
Yeah, thanks, Peter. It's great to be back. Unfortunately, we can't see each other in person, but this is the next best thing.
Yeah, I know. I mean, we certainly will and get together in person soon, I'm sure. There are so many things I wanted to talk about, and I think last time we spoke, we focused mostly on our mutual favorite drug, rapamycin, and our favorite pathway, the mTOR pathway, and certainly for those listening, I don't want them to think we're not going to touch on that today. We absolutely are. But I want to start even broader than that, because so often you and I are having these discussions about all things that pertain to aging. And, I find you to be one of the most thoughtful people across the topic. So I sort of want to start with these broader questions about aging. A lot of people have different definitions of aging. And truthfully, I'm not sure I even know how to define aging sometimes. It depends, I guess, on the context in which I'm asked, right? I think if my 5-year-old asks me about aging, I would come up with one answer. And if I'm giving a keynote talk and somebody asks me about aging, I'd have to give a different one. So what are some of the ways that you really describe aging?
Yeah, so that's a really good question. And I think, I would probably say the same thing that you just said, which is that I'm not sure I have a great answer, and it changes depending on the situation. I think in the past, I often gravitated towards sort of a molecular definition of aging. So, what are the types of damage that occur during aging? What are the consequences of that damage? Sort of a, in some ways, a hallmarks of aging framework view, right? Where we know that things like mitochondrial dysfunction, telomere shortening, cellular senescence, things like that happen during aging at the cellular and molecular level and contribute to many of the functional declines and diseases that go along with aging. And so, given my training in biochemistry and molecular biology, that sort of is the natural place where I go when I think about, what is aging. I would say, over the last several years, I have developed I think a greater appreciation for a functional definition of aging. And so as I start to think more and more about translation of interventions that seem to affect the biological aging process in laboratory animals outside of the laboratory into the clinic, I spend a lot of time thinking about, well, what are some of the functional changes that go along with aging? And we know that across every organ system in the body, we see functional declines that go along with aging. And so I've started to think more about, things like frailty as an important component of defining aging from a biological perspective, when we're talking about having an impact on health and longevity. So I think it really depends on the context. I guess the other thing I would say is both of those definitions and the way I almost exclusively think about aging, unless somebody sort of forces me out of my box, is from a biological perspective. There are other aspects of aging that intersect with biological aging, right? That are probably as important as what I think of as fundamental biology of aging to quality of life. So social aspects of aging, for example, are extremely important in people, especially, right, for quality of life as you get older. I don't tend to gravitate towards, that kind of a definition of aging, but I do recognize that it's important. So, I think I'm naturally always thinking about the biology of aging, and as I already said, I tend to focus on the molecular mechanisms that drive the biological changes that go along with aging.
So let's look at the sort of two extreme views within the biologic and then kind of try to figure out where disease fits in. So on the one hand, you referred to the hallmarks of aging, and there's a very famous set of papers that have laid these out. And if the day comes that I can actually recite all of them, I'll be very impressed. But I always have to look it up, right? But
I think I can probably get 7.
Yeah. It's like, so you mentioned a bunch.
Who can name the most hallmarks of aging, Matt or Peter?
DNA damage is one of them. Cellular senescence is another. Stem cell fatigue is another. Protein misfolding is another. Telomere shortening is another. Mitochondrial dysfunction is another.
My favorite.
Let's see. Did I mention nutrient sensing issues?
No, deregulated nutrient sensing. Yeah.
So that's my 7. What am I forgetting?
There's intracellular communication.
Bingo.
And what are we missing here? I'm going to be really ashamed if it's something that I study.
Yeah.
But yeah, so we got 8 out of 9. That's not bad.
You've got those. And then at the other side, you talked about, okay, let's talk phenotype. Let's talk about the outward expression within the organism, and frailties, I think, a fantastic example. Where does disease fit into this, right? Because with aging comes more cancer. With aging comes more cardiovascular disease. With aging comes more dementia. And you could argue that those are functional. Maybe less so cancer, but certainly cardiovascular disease and dementia are very functional forms of decline. But of course, at their root, they have a very cellular component and a very strong set of cellular contributions. Do you think of disease as basically the bridge or the link between these fundamental cellular declines and the ultimate phenotypic declines?
No, I would not say they're a bridge. So I think that I actually personally tend to think almost the other way around, where I think that the functional declines that often precede overt disease or clinical diagnosis of disease are probably as important or more important from a quality of life perspective as we get older. And this may simply reflect the fact that I'm getting older, and I've noticed some of these functional declines in myself, right? And I think these functional declines happen, as I already said, in every organ, every tissue. We don't always recognize them as such unless we sit down and think about and try to, list out all of the ways that we have changed as we get older. But I think, and those often happen far before you get diagnosed with any age-related disease, right? So I'm pretty fortunate. I turned 50 in February. I don't have any age-related disease, at least that I've been diagnosed with. Yet I have a multitude of functional declines, which fortunately don't impact me severely, but that I recognize I'm functionally impaired to where I was 25 years ago. I think it's just a fact. Any 50-year-old is. And so I kind of think of those as the first sort of things that you can observe that happen during aging, often way before you get an age-related disease. The other thing I would say about disease, so there's actually 2 points I want to make. One is, I think it depends on the disease, but we really don't have a good understanding of when the pathology of the disease is no longer normative aging. And what I mean by that is, we've got some understanding of the molecular cellular mechanisms that drive biological aging that contribute in some way to our risk of developing Alzheimer's disease, cardiovascular disease, sort of all of the age-related diseases that are major causes of death and disability. But in most of those cases, there comes a point where the pathology of the disease is not necessarily at a molecular mechanistic level an extension of aging biology. It becomes something different. And I think that's really important to recognize, because one of the implications of that is that an intervention that affects biological aging, let's just say rapamycin, we can discuss whether rapamycin really affects biological aging in people. I think that's still a little bit of an open question. Let's just say, for the sake of argument, that it does. It's not clear that that same intervention is going to be effective once a pathology, progresses to the point that it's not the same mechanism anymore. So I think that's a really important point that sometimes gets lost in this discussion of aging and disease.
So let's actually double click on that using a disease. So you want to pick one of the big 3: atherosclerosis, cancer, dementia.
I think cancer is a really good example, right? So we know mTOR, and I'll go back to rapamycin in part because, it's, again, something I think a lot about, but it's a really good, I think, example in this specific case, because we know that mTOR, which is the target of rapamycin, right, the protein that rapamycin inhibits, plays this fundamental role in regulating cell division and cell cycle, right? So if you inhibit in a non-cancerous cell, if you inhibit mTOR enough, you will stop the cell cycle. The cell will stop dividing, right? But there are mutations that can happen that lead to cancer that cause the cell to no longer pay attention to the mTOR break, right? And so once that's happened, if that's the type of cancer you have that no longer responds to mTOR inhibition, rapamycin won't do anything to cell cycle in that case. So that's a really, I think, specific example that you can point to. There are sort of an infinite number of other examples that we could use, but that's a really nice one because there, rapamycin will be quite effective at preventing cancer before that mutation happens. But after that mutation happens and the cell's not responding to rapamycin anymore because it doesn't sense the mTOR break, it's completely ineffective, right? So that I think is a case where the mechanisms have changed, right? The mechanisms that are important for preventing cancer before that mutation occurred are different from the mechanisms that might deal with that cancer after that mutation has occurred.
Yeah, it's funny. This is a little off topic, but I've often contemplated this question in the context of nutrition, because in as much as there's an optimal nutrition to prevent a condition, it might not be the same as the optimal nutritional strategy to treat the disease once it's present.
Yeah.
And an example of that in an extreme sense might be a ketogenic diet. I happen to believe a ketogenic diet is probably the best treatment for someone with type 2 diabetes. Because of course, type 2 diabetes by its very definition is a carbohydrate intolerance disorder. So once a person has it, you pull out the carbohydrates completely and you let them heal, right? You basically let them recover and regain their ability. And again, we've seen that people who have been on a ketogenic diet for a long enough period of time can resume some amount of carbohydrate consumption, provided their other factors are changing, such as exercise. Does that mean one needs to be on a ketogenic diet to prevent diabetes? No, I don't think so. So it's a little bit of the same idea, though it's still something that's unclear. One thing I want to go back to on the disease front is, and I believe it was Cynthia Kenyon who spoke about this once. I think I read it in a paper, something to the effect of, using a disease-based definition for aging is, she didn't use the word tautology, but she effectively said it is a bit of a tautology, because at what point is a disease a disease? It's only a disease when some people have it and some people don't, right? If everybody has cancer by a certain age, then it's normative aging, to your point. It's no longer a disease. Yeah. And then we get into, well, what does it mean that why do 0.0004% of the population live to be 100? They've managed to not succumb to a disease by by the age of 100. And what does that tell us about their normative aging versus everybody else? All of this is to say, I literally still don't think I understand what aging is, which is unfortunate given my line of work.
Well, I mean, I think we have to just accept that it's extremely complicated, right? And so you're never, I shouldn't say never. I don't think I will ever understand aging fully, and I don't think the field will, at least in any time frame that I can expect to experience, right? But I also believe that we don't have to understand it fully to be able to have an impact on the biology of aging through interventions. And so I think and that's kind of where I'm at. I feel like I've got a conceptual flavor for what aging is, and I have some information about what the molecular mechanisms are, and it's enough information that I can come up with rational approaches to target those mechanisms with the prediction that those approaches should have an impact on health and longevity as animals and people get older. And then we have to test those predictions, right? That I think is that's kind of the way I think about it. I do want to come back to one point though, which I also think is often underappreciated in this relationship between disease and the biology of aging. I think, sometimes people get into this debate about whether or not the biology of aging causes diseases of aging, right? So does the biology of aging cause Alzheimer's disease, cancer, cardiovascular disease, right? People get in debates about that. And I personally think the data are pretty good that what I think of as the biology of aging, the molecular mechanisms, the hallmarks, whatever you want to call them, contribute in a causal way to your risk of developing diseases. But I also think it doesn't matter. It does, and this I think is really important. From the perspective of what is the best strategy to keep people healthier longer, it just doesn't matter whether aging causes disease or it creates a permissive physiological state for disease. You can't argue that biological age is the single greatest risk factor for every major cause of death and disability in developed countries. That is just a fact. And whether or not biological age causes those diseases or creates a physiological state that allows those diseases to manifest themselves doesn't matter from the perspective of what is the most effective way to prevent those diseases. And I think that's where this debate is counterproductive, right? Should we call aging a disease? Does aging cause disease? I think that those are not the right questions to be asking in my view.
Yeah, let me see if you would agree with my assessment. I think you would, but I'll tell you how I think about this problem clinically, right? So let's use atherosclerosis as an example. And I want to highlight what you just said in case the person watching this or listening to this missed it in any way, shape, or form. There is no, and this is one of the questions when I used to give talks, I'd always lead with a question like this. What is the greatest risk factor for atherosclerosis? Hand will go up. Yes. Smoking? No. Hand will go up. High blood pressure? No. Hand will go up. If it's an especially, erudite audience, ApoB or LDL-C? Nope. And they'll just keep rattling. Inflammation? Nope, 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 nope. The number one thing is age. Hands down,
yeah.
Right? You take a 70-year-old person who has everything perfect about them, and you compare them to a 20-year-old train wreck who has not a single thing that is in their favor. There is no comparison about their 10-year mortality prediction. The 70-year-old is in hands down a worse shape. So yeah, you can't undo that. Now, here's how I think about this problem clinically. Atherosclerosis is a great example because it's the disease that we understand the most of the big three, right? Which is not to say we understand it completely, but we have a far better understanding of what its drivers are and how to prevent it than we do cancer and Alzheimer's disease. Lowering ApoB, pharmacologically, nutritionally, et cetera, is arguably the most important strategy you have to reduce it, along with probably improving metabolic health. So those two things, right? So regulating glucose, insulin, lowering ApoB, all of these things can be done through lifestyle, through drugs, et cetera, can dramatically reduce a person's risk of atherosclerosis. None of those things are necessarily directly targeting the 9 hallmarks of aging. I think indirectly they certainly do, but when you give somebody a PCSK9 inhibitor, which specifically targets a protein that allows the body to clear more ApoB particles out of circulation, it is by no means targeting one of those 9 pillars, but it's having a measurable impact on reducing their risk of disease. And in the end, that's the part that I think is hard for some people to understand within the aging community, is that you can still target metrics of a disease specifically without going after a hallmark.
Sure, and I think I don't disagree with you that I think that it's a concept that sometimes is underappreciated, right? Especially within the aging community. I also think it makes sense, right? So even if the hallmarks, or we focus so much on the hallmarks because it's easy, right? I think there are some reasons why the hallmarks are incomplete, but let's just keep using that term sort of as a surrogate for the molecular mechanisms of aging, right? If we accept that the hallmarks are at some level, preceding the damage, whatever that is, that's causing the disease, it makes sense that you could intervene sort of, if we think about it in an upstream, downstream perspective, right? The hallmarks being upstream, the disease being ultimately downstream. It makes sense that you could intervene at the level of the hallmarks. It also makes sense that you could intervene, in whatever the bridge is that's connecting the hallmarks to the disease, you wouldn't necessarily impact the biology of aging at all. And this gets back to what I was talking about before, which for many diseases of aging, there comes a point where the pathology of the disease is not normative aging anymore. And so you can quite successfully treat or cure a disease of aging in an individual without impacting the biology of aging. In fact, I would argue that's almost exclusively what is done clinically, right?
Yep.
Is to try to either alleviate the symptoms of the disease or cure the disease. There's starting to be more on the preventative side, but I still think that lags far behind, waiting until people are sick and then trying to do something about their disease. But you don't have to impact the biology of aging to be successful at any of those things. I would just argue that impacting the biology of aging is going to be a much more effective and efficient approach from sort of the overall health perspective. I think the other point that's obvious but is important to make is if you don't target the biology of aging, that you're really only impacting that one disease. Say it's cancer. You can cure somebody's cancer, you can take the tumor out, right? And they can go on and live a normal life. But you haven't done anything to the biology of aging. If you don't confront the biology of aging, right, you still have all of these other functional declines and diseases of aging that are increasing, essentially exponentially as you're getting older. And so the effect on health and longevity is quite small. In fact, I think J.L. Shansky was the person who originally kind of did the math here, right? And it's really very striking. So if you consider a typical 50-year-old woman in the United States, and you say, what would happen if we had a cure to all cancers, right? Every type of cancer, we had a cure today, and we implemented that. Life expectancy for a typical 50-year-old woman in the United States would go up about 3 years. That's it. So we've won the war on cancer. We get a +3 on life expectancy. It's about the same for curing heart disease. If you cure both of those diseases, it's roughly additive. It's, I think, about 7 years. So the impact on life expectancy is actually, from curing disease, is actually quite small. If you compare that to the impact of targeting biological aging, which again, I think we have to be honest, right? This is hypothetical in humans at this point. So all we can really do is extrapolate from what is done in laboratory animals. But it's pretty routine now. There are, I don't know, maybe a dozen, 15 different interventions that can increase lifespan, slow aging in mice by between 15 and 30%. If we just extrapolate that to the human condition, the impact on life expectancy is about 20 years, with the added value that because you've sort of slowed all of the functional declines of aging simultaneously, those extra couple of decades are spent in relatively good health, right? So I think it's just important to appreciate the potential difference in health and life expectancy from targeting aging as opposed to what we do right now, which is trying to cure individual diseases. And I've sort of adopted the term, I think of that as 20th century medicine, the disease first approach, or I would even say 19th century medicine. We've been doing this for a long time, right? And I contrast that to what I think of as 21st century medicine, which is approaching health and longevity from the perspective of the biology of aging. And we're not there yet, right? But I do believe that this is happening. There is a transition occurring, a slow appreciation among the broader clinical community of the potential of this kind of approach. And I do believe that we will get there in this century. So it is my hope and expectation that 21st century medicine will really become targeting the biology of aging to enhance health and longevity, hopefully by much, much greater amount than we're currently able to do.
Yeah, so I agree with a lot of that. The one thing I would throw a little bit of a question at is, and I'd love to have Jay on the podcast because I don't know that I fully agree with his analysis. I agree with the spirit of his analysis. So I completely agree that disease-based whack-a-mole is not going to be nearly as effective as targeting the basic biology of aging.
Yeah.
So completely agree with your points. I don't know that I agree with the magnitude, right? The de minimis magnitude of it, because I really think that Jay's analysis is focused on an independent look at each disease, whereas in reality, if you eliminated cardiovascular disease, by definition, you have reduced inflammation significantly. You've reduced the burden of microvascular disease significantly. Those are going to play into other diseases. So, his analysis is very actuarial, but it's not actually very biological. That's my opinion. Now, again, I should have...
I think that's fair. Yeah, I think that's fair. I think you could make the case, at least for cancer, that it may be closer to,
I agree.
Just what the straight, math would suggest.
Yeah. Now, with all of that said, I couldn't agree more with the macro point here, which is delaying chronic disease is probably not going to be as effective as targeting something at the foundation. Now, that said, let's take a look at Neer's data, right? So when you look at Neer Barzilai's work with centenarians, the overwhelming statement here is they get chronic diseases later. They don't live longer with them. And I remember, really being struck by that. It was not necessarily my, that would not have been my null hypothesis going into Neer's, a study of Neer's work, and Tom Pearl's as well. Between Neer and Tom, you really have the greatest assessment of the centenarians and their siblings.
Yeah.
And you realize that they don't seem to have magical protection from a disease once they get it. When they get cancer, they're just as hosed as the rest of us. When they get heart disease, they're just as bad off as the rest of us.
Yeah.
But they get a phase shift. They get a 20-year, sometimes 30-year phase shift in when they're going to get the disease. And so how does that factor into my thinking clinically? My factoring into that clinically is the sooner you begin prevention, the more you can mimic the centenarian. What we don't fully understand is molecularly, why is that the case, right? We've identified some of their genes, right? We know that, they're going to be more likely to, have ApoE2 versus ApoE3 or ApoE4. They're going to be, less likely to have ApoC3, high regulation versus low. I mean, there's, you have a lot of genes that produce phenotypes that are favorable. But when you bring it back to our 9 hallmarks, by the way, the 9th hallmark is epigenetic modulation.
Of course.
Yes, it's the epigenetic modulation. Yeah. Now, the other point, I guess, that we're both well aware of, but maybe for the listener, is how difficult it is to study aging in humans targeting the basic biology, because you don't get to do what our clinical trials apparatus is set up to do, which is pick a disease, a very clear endpoint, and target it. If your endpoint is nutrient sensing, that's a tough clinical trial.
Yeah. So I agree, and I think we should definitely come back to that point, because it's clearly a major focus of the field right now. Is how do we start to test some of these interventions that we know work in laboratory animals in the clinic? That's a challenge. I want to come back to your comment about centenarians, though, because I think this again is it's a conceptual area where there's a lot of I think misunderstanding, both among people in the field and also lay people who pay attention to the field. So you're right. I think that the bulk of the evidence supports the idea that centenarians do not live longer with multiple age-related diseases, but they have genetic risk factors or genetic variants that put them at lower risk, at least for the major killers. So there is a genetic component to being a centenarian. It's not huge, but it's significant, probably somewhere, I think, around 25, 30%. And they tend to not have the high-risk genetic variants for Alzheimer's disease, certain types of cancer, heart disease, things like that. And then there's a luck or environment or something else we don't understand, right, that comes into play. But people often look at that observation and make the assumption that we don't see variants in things like mTOR or sirtuins. Not that there aren't variants that haven't been talked about, but that have strong effects, right? So I think the question becomes, why don't we see variants in, SIRT6 or mTOR, or pick your favorite longevity gene, FOXO, right, that cause people to live to be 180 years old? Because we can do that magnitude of lifespan extension in a mouse or a C. elegans, right? And so they go from that. So that's an observation. We haven't found those variants yet.
Although FOXO is one of the genes, FOXO3A, no, it's not. You're right. It's a very weak effect, but it's clearly a higher amount of.
As is SIRT6, right? And as is mTOR. There's evidence for all of those things. You can find genetic evidence, but the effects are relatively small. So then the interpretation that people make is the reason we don't see those variants is because humans are fundamentally different from mice or whatever your favorite laboratory organism is, and none of those things will work the same way in people. Now, I can't prove that they will work the same way yet for aging in people, but that's not a logical sort of interpretation, right? I would argue the reason you don't see strong effect variants in mTOR, for example, in people, is because we know that strong effect variants in mTOR are incompatible with life and development. Even in mice, right? You make a mTOR knockout mouse, it's dead. So I think the reason why you don't see these strong effect variants in people is because there is such a strong selective pressure, either they don't make it through gestation, they don't make it through development, or they're sterile, right? All of those are incompatible with evolutionary success. And that's my hypothesis for why we don't see these very strong effect genetic variants in people that lead to 160, 170 year lifespans. Again, it's a hypothesis, right? It's hard to know what the explanation is, but it certainly fits with what we see in laboratory animals. Any of these mutants in mice that have 30, 40% lifespan extension, I mean, they are all significantly defective from an evolutionary perspective, right? They would not be selectively advantageous mutations. And so I think that's at least a consistent explanation for why we don't see these what we would think of as slower aging variants pop up in people. The other point that's important to make as well, though, is that doesn't mean that we can't intervene in these pathways to have an impact on health and longevity. And for me, this has been, probably the most exciting aspect and development in the field over the last probably 15 years. If you asked me 15 years ago whether I thought that it would be easy to slow aging in an old mouse, I would have said no. I would have said you probably have to start, at 6 months of age and treat them all the way through life to get the benefits. And that was honestly largely based on caloric restriction, right? Which that seems to be the case for caloric restriction. What has emerged now is there are 5 or 6 or 7 or maybe even more different interventions that can be initiated in middle age or even in late age in mice. And you actually it's not only that you slow down the declines, you actually reverse the declines, right? And again, I come back to rapamycin because in pretty much every tissue where this has been looked at, you take an old mouse, you give it rapamycin, functionally it's younger in that tissue or that organ. And lifespan is extended.
And by the way, to your point, Matt, I was having dinner with a friend last night who asked me, why don't we start giving rapamycin to children? And I said, look, I think rapamycin is the most important, gero-protective agent out there today, but you wouldn't want to give it to a developing child, right? He said, if you had to guess when would be the right age to start, I said, I have no honest clue, but it wouldn't be before 25, right? It just wouldn't be before about the age of 25, which speaks to your point. Any genetic manipulation, or in this case, naturally acquired genetic variation that mimicked rapamycin would probably not be selective because you wouldn't be able to turn it on and off the way you would need to with the drug.
That's right. Yeah, that's right. And I think that's a really interesting question about rapamycin and other interventions as more and more interventions start to, get to the same sort of level of confidence that we have about rapamycin. When is the optimal sort of treatment period, right, to get the biggest benefits? And I think, again, this is it's not something that often gets, I think, talked about in that conversation, but it's really it's a balancing act, right? Any intervention is going to have some risk associated with it, right? The risk can be low, the risk can be high, but there's always some risk of side effects. And so the question of optimal treatment, right, is a balance between the beneficial effects that you get and the risk of detrimental effects, side effects. And so I think we still don't, even with rapamycin, we still don't have a great feel for what that risk looks like, right? And that's in part because, you know, we haven't had long-term controlled clinical trials at multiple doses, multiple strategies of you know, intermittent versus continuous treatment, things like that. So we just don't know, right? And it's interesting in the case of rapamycin, because my impression is that, you know, there are a group of people, I think you and I both know some of them, we might even be among them, who you know, have self-experimented, right? And my impression is that there has been a movement towards the idea that, you know, once a week dosing with rapamycin is probably better than daily dosing with rapamycin for aging effects in people, and that, you know, you might want to do it for 3 months and then you stop for 6 months, or you do it again for 3 months, right? I think that's where people are starting to coalesce around this idea. There's not a lot of data to support that, right? It's a guess, and so. So it's just interesting to sort of see how that, you know, is evolving in the absence of long-term, large-scale controlled clinical trials. And this is getting to the point that you raised earlier, which is it's really hard and expensive to do long-term controlled clinical trials for aging in people. We really, I think, still as a field don't have a great strategy for how to address that challenge of actually trying to answer some of these questions in the way that, you know, at least traditionally we would want to see them answered in a clinical setting.
I mean, I think there's an even bigger problem, Matt, which is I don't think there's a regulatory appetite to even do what would be necessary, because we have the regulatory appetite to say you take an individual who is either at very high risk for a disease or already has said disease, and we will go ahead and accept the risk of a clinical trial to assess it. But by definition, if you truly want to understand how gero-protective metformin or rapamycin or canagliflozin or pick your favorite molecule is, you really need to be testing it in people before they have a disease.
Yep.
So even if you, so there's really two fundamental problems. This is one, we do not have a regulatory environment that accepts that risk. So I would love to see the IRB submission that says we're going to test rapamycin in healthy 50-year-olds who are, you know, whose 10-year risk of death is less than 1%.
Yep.
And then secondly, because we can't logistically follow those people for the next 50 years, which is what would be necessary to understand its true magnitude of geroprotection, we would need really good biomarkers of aging, of which I will posit, and you may disagree, we have somewhere between 0 and epsilon of those. I mean, we don't have diddly squat in the way of meaningful biomarkers of aging. By the way, I want to go back to your point on Rapa. So you know, as you do know, and I'm very happy to talk about, I mean, I've been taking rapamycin for 2.5 years now, and I am one of those people who has coalesced around once weekly dosing. I have fiddled a little bit with my dose. I've varied it from as little as 5 to as many as 8 milligrams once a week. I've also done the cycling on and the cycling off, but I am completely flying blind. Most of my dosing and frequency data comes from Joan Manick and Lloyd Klickstein's 2014 paper with everolimus, which of course is not the same as rapamycin, but it's a pretty reasonable hand-drawn facsimile of it. And it was from that study that I concluded that, you know, 20 milligrams versus 5 milligrams versus 1 milligram, your sweet spot was at about 5 from a side effect standpoint and an efficacy standpoint, and the daily dose of 1 milligram didn't seem to produce as good an effect as the 5 milligrams once a week. But how does that stand in comparison to what we learned from all of the ITP studies where it's continuous administration of rapamycin? And to your point, because we'll come back to these and talk about them, remarkable results regardless of when it's initiated.
Right.
I don't know what to make of that.
I mean, and you know, I kind of agree with everything you said about why, you know, if you're going to pick one regimen for rapamycin, that makes sense. And like you said, it's really based on 2 clinical trials, right? I mean, really.
Yep.
And so it's a limited data set, but at least for immune function in people, you know, it seemed to work. And that's actually, I mean, you know, we could spend hours talking about this, because that's a whole nother, I think, interesting and informative sort of experience was the failure of the phase 3 clinical trial at Restore Bio, right? And what happened there. And I don't think we actually, it's at least not it's not published yet.
Well, let's talk about this because it is really interesting. So let's back up for a moment and give people the context. So when Joan was at Novartis, and both Joan and Lloyd were at Novartis in 2014, the everolimus study was done. And do you want to just tell people really briefly what that study looked at?
Right. So that study, so everolimus is a derivative of rapamycin, and biochemically it has exactly the same mechanism. So it's at least I conceptually think about them as essentially the same molecule. So anything that we see with everolimus, we would expect to see with rapamycin. And so that was a phase 2 clinical trial in healthy older adults to look at whether or not a 6-week treatment with everolimus could boost vaccine response. So the ability of older adults to respond to an influenza vaccine. And that actually was based on one of my favorite papers from Pan Zheng's lab at the University of Michigan, who showed that in mice, I think it was 4 weeks of rapamycin. It was either 4 weeks or 6 weeks of rapamycin in old mice boosted the ability of a flu vaccine to protect those mice against a lethal dose of influenza. That, if anybody hasn't looked at that paper, I would just encourage you to go check it out. I think it was a 2009 Science Signaling paper from Pan Zheng's lab. The title has something about hematopoietic stem cells and rapamycin.
We'll link to it in the show notes for sure.
Okay, yeah, it's an amazing study, but my favorite experiment there was this experiment where they took young and old mice and they gave them a influenza vaccine, and then they waited 2 weeks, and then they gave them what would be a lethal dose of influenza if they hadn't got the vaccine. And in the old group, half the mice either got rapamycin or they got a control, right? So the first thing that struck me about that experiment was, if you look at just the difference between young and old mice who got the vaccine, all of the young mice were protected, 100% vaccine response. I think it was about 65%, so 2/3 of the old mice did not have a sufficient response to the vaccine that they were protected against influenza, right? And I don't know if the numbers I don't think the numbers are exactly the same in people, but there is definitely that same trend where older adults tend to not respond to vaccines as robustly as younger adults. Unless those old mice got rapamycin. If they got 6 weeks of rapamycin, they were 100% effective at responding to the vaccine. So at least for that measure of immune function, rapamycin fully restored the immune system back to that of a youthful immune system. So that was the mouse data that sort of served as support for testing this in humans in this clinical trial that we're about to get to.
And by the way, Matt, do you recall if the immune response in question, i.e. the immune response that was better in the Rapa group versus the non-Rapa group of older mice, was this a B cell response, a memory B cell response, or was it a T cell response?
I don't recall the data. I know they have a lot of data in there looking at the antibody titers and different types of immune cell types and how they responded. As I said, the title of that paper and the model that they proposed was that rapamycin was acting at the level of hematopoietic stem cells to rejuvenate hematopoietic stem cell function in some way. I don't recall the details of the immunology, and I've tried multiple times throughout my career to become fluent in immunologist speak and have failed miserably every time. So that's a weakness of mine that will likely never be addressed adequately.
It's just got such amazing implications for what we're seeing with COVID vaccination, because we are still in such a nascent stage of truly understanding. I mean, we're seeing people who naturally acquired COVID who within 6 months have no more circulating IgG. And we have no clue if they still have immune function. For example, do they still have memory B cells in their bone marrow that when challenged will make antibodies? Do they still produce, do they still have memory T cells that will show up and immediately respond? And so we're actually involved in a study that's looking at that. But my intuition is you can probably still have an immune response or an immune response that's ready to go absent circulating IgG.
Yeah, the one thing I will say about rapamycin and everolimus is that it seems like it's not one simple mechanism at play. So Joan, for example, has published data that one of the effects of everolimus and another drug called RTB101, which is also an mTOR inhibitor, is to boost antiviral gene expression, right? And we know also that rapamycin, at least in mice and almost certainly in people, tamps down on the sort of, chronic sterile inflammation that goes along with aging through mechanisms that still are being worked out. So I think it's probably multiple things that are going on that can impact immune function in different ways, right? When you treat with rapamycin, especially in the context of an old animal or an old person. So it's probably not going to be one mechanism is my guess.
So based on this study, so Joan and colleagues take a group of, I believe, 65-year-olds. I think they're 320 of them. So divided into 4 groups of 80. You've got a placebo group, 1 milligram a week group, 20 milligrams once a week, and 5 milligrams once a week. Yeah.
That's right. Yeah. And so they did I think it was a 6-week treatment period. And then they also waited, I think, 2 weeks. And then they gave them a flu vaccine. And what they showed, I mean, obviously it's people, so you can't do the mouse experiment and then give those people a lethal dose of influenza. So they were sort of, stuck with looking at things like antibody titers and to try to get an assessment of, did the people who got everolimus respond better to the vaccine than the people who got the vehicle control. And it looked like they did. And it was, you can argue about the strength of the data. I think it was pretty clear that they had, at least at the 5 mg once a week, and I think the 1 mg daily, I can't remember, maybe it was the 20 mg once a week, but the 5 mg once a week looked pretty convincing that they had a better response to the vaccine. I think the other thing that's really important about that paper is that the incidence of side effects was really hardly different at all between the different everolimus groups and the placebo, and particularly the 5 mg once a week. There really was no significant increase in adverse events in that group, which gets back to how we kind of started on this tangent, which is that's part of the reason why, I think people are moving towards the idea that you can still get efficacy from once weekly dosing, and that the side effects are reduced at once weekly dosing to essentially 0 or close to 0. So that was the first phase 2 trial. And then they went on and did a second.
Before we leave this trial, Matt, I think it is important for someone listening to understand why people like you and I and Dave Sabatini and all the people who live in mTOR land, I'm not putting myself in the same category as you guys, but you know what I mean? I'm an mTOR fanboy. Why was that such an interesting and landmark paper? Well, I think it's because up until that point, the only human application for rapamycin was immune suppression, right?
That's right.
Rapamycin is a drug I have known about forever because as a surgical resident, I was giving rapamycin to kidney transplant patients, heart transplant patients, and liver transplant patients, along with a cocktail of cyclosporin, prednisone, MMF, all of these other really nasty drugs. And it was one part of that in their ability to suppress the immune system. So I think prior to that paper, you have the ITP, the first ITP that came out in 2009, suggesting this is a remarkable tool for longevity, at least in the ITP mice. But then on the other hand, you're saying, well, but it can't really work in humans because it's going to be really horrible to the immune system. So you had this sort of dialectical dilemma, which all of a sudden it became, well, maybe that's not the case. So how do you reconcile the data that we saw in Joan's paper with the fact that rapamycin is, at least in theory, an immune suppressor as it pertains to organ transplantation?
Yeah, and I think, you're absolutely right. That was one important aspect of that paper. And I unfortunately think that the old view, which in my room is the wrong view, that rapamycin is an immunosuppressant, still is prevalent in the clinical community. I think most clinicians still think of rapamycin and rapalogs as immune suppressants, because that's often how they're used clinically to prevent organ transplant rejection. My so I think the simple answer is it's all about dose, dummy. I mean, we know every drug has a dose response, right? And that you can get different effects, different outcomes, different side effects, depending on the dose. And so, when you back off on the dose of rapamycin or everolimus, in the context of an aged physiology. So there's multiple things going on here in that study. They used lower doses. They tested once weekly dosing, and these are old people who show a functional decline. You're not going to see a functional improvement in vaccine response if you did this experiment in young people, right? You're only going to see it in the context of older people where they already have a functional deficit. And that's, again, it's an important conceptual point that I think often gets lost in these discussions. The other thing to appreciate about how rapamycin has been used, traditionally, and how it was first approved is these are people who had an organ transplant, right? Taking high doses of the drug, and also, I think always, I'm not an organ transplant physician, but my impression is these people are always taking other immune suppressants in combination with mTOR inhibitors. So in that context, yes, it does seem to be the case that mTOR inhibitors can help reduce the chance of organ rejection in transplant patients. I could be wrong. I think there's preclinical data. I don't know of any strong clinical data that by itself, rapamycin, even at higher doses, has substantial immune suppressing effects. It might. It wouldn't shock me if it does at high doses, but I don't know that that's really ever been shown clearly in healthy people, taking higher doses of the drug.
Yeah, that's interesting. I don't think I've ever gone back and looked at the FDA approval process in '99 because obviously it was approved for that use, and I think that's the only use that it's been approved for. So I wonder what trials led to that approval. Whatever trials would have taken place in the mid '90s.
Yeah, I don't recall. Another point that I think is worth making is, we use, and I'm as guilty of this as anybody else, we use sort of broad terms when we're talking about the immune system, suppression, lower function. We say the immune system, doesn't function as well in older people as compared to younger people, which is true. But I think when we say doesn't function as well, we tend to think of as it's functioning at a lower level, right? There's just less activation, which actually isn't necessarily the case. In old mice, in old people, there's a lot of immune activation that shouldn't be happening, right? There's a lot of sterile inflammation that's occurring. So it's not necessarily that the immune system is functioning less, it's functioning inappropriately. And I think there's a ton of evidence that many of the benefits that we see in mice from rapamycin occur because it tamps down on that sort of sterile inflammation that goes along with aging, right? The inappropriate activation of the immune system. So in that sense, you could think of it as an immune suppressant, but through mechanisms that I don't understand at all, and I don't think anybody really understands, it seems to be more effective at targeting the bad part of the aberrant immune response in an aged physiology, which might be the reason why you're able to then have more of the good part. And here I'm, clearly showing my ignorance of immunology because I'm referring to it as bad and good, right? But I think in some ways it's useful to kind of think about it at that level because it's easier to appreciate that it's not, not immune function isn't intrinsically good or bad, right? It is. And there are different types of immune responses. And if you get the wrong type of the immune response at the wrong time, that's bad. If you get the right type of immune response when you need it, that's good, right? And I think in the context of aging, we just see a lot more of the bad and probably a decline in function of the good. And I don't know if rapamycin is affecting both of those, but I think it's definitely affecting the bad and bringing it back down, which might just be enough to allow the good to come back up where it's supposed to.
Yeah, which, look, I think that's a great point to make. And it's very similar with reactive oxygen species, right? I mean, you have to have them. They are vital signaling molecules. And yet if they run amok, they cause damage. And so, yeah, a lot of biology is in the Goldilocks framework of not too much, not too little.
Yeah. Can I just throw one more thing out there as well, which is, and this is again, I'll admit, if you'd asked me 15 years ago, like how important did I think that, chronic inflammation and immune function would be in aging, I probably would have said, I don't know, but my guess is it's not going to be the major player, right? Because, my background came from working in yeast and worms, which, worms sort of have an immune system, but not really, right? Where I would have pointed to things like translation and autophagy and mitochondria, all of which are clearly important for affecting inflammation and immune function. But I wasn't really bullish on inflammaging at that point. And I have become very bullish on inflammaging as, critically important for many of the functional declines and diseases of aging that we see in people. The point that I want to make here is that maybe I shouldn't say all of the interventions that I know about that I'm enthusiastic about translationally seem to hit inflammation in mice, and they seem to tamp down on the chronic sterile inflammatory signaling that we see go along with aging, which makes sense. It's encouraging, right? That they all seem to have this shared mechanism. But the flip side of that is people talk a lot about people are very excited now about senolytics, or reprogramming now is the new senolytics, right? It's the thing everybody's excited about. I'm not sure that those are fundamentally different from rapamycin in terms of the way that they're working, and I think we need to find out, because it would be nice to know whether combinations of these interventions are going to do better than one alone. But to me, the underlying theme that seems to be similar about all of these things that work in mice is, if you look in tissues of aged mice at, inflammatory cytokines, P16, P21, markers of senescence, they seem to be tamped down by all of these interventions, which might explain the functional improvements that we see from using these interventions in aged mice.
Yeah, I think that's actually a really interesting point. And I would kind of say I'm in the same boat. I have become probably more convinced at the importance of inflammation, certainly in Alzheimer's disease and certainly in atherosclerosis, because I've seen enough people who either develop these conditions without otherwise clear reasons for it, and vice versa, right? People who do have other risk factors and don't go on to develop, but have, at least have a demonstrably low measured amount of inflammation. Again, the question becomes, is there a direct target of inflammation, or do you simply reduce inflammation by targeting these other mechanisms, which we'll get to? Let's go back to the everolimus progression. You were just about to talk about RTB 101. So what is that, and how is that the next stage in the evolution of this rapalog? Right.
So there was the first phase 2 trial was done. They hit their endpoint. It looked like it worked, and they didn't see any. I mean, this was a phase 2 trial, so the important thing was they didn't really see any substantial adverse effects as well, right? So then for the next trial, they added in another drug called RTB 101, which is one of these drugs that hits multiple kinases in the cell. So mTOR is a kinase, which means its biochemical activity is to put phosphate groups on other proteins, but you can think of it as a signaling sort of activity, right? So mTOR senses the environment and regulates the output based on this signaling function of being a kinase. This drug, RTB101, inhibits mTOR, the catalytic activity of mTOR. It also inhibits other kinases. So it's talked about as sort of a dual kinase inhibitor, but in reality, it hits multiple kinases. So it's a dirtier drug. That's maybe the point to make. It's a dirtier drug than rapamycin, which has a very specific biochemical effect on mTOR and mTORC1 specifically, which we haven't dove into the mTORC1 versus mTORC2 situation yet.
And was the rationale for using a dirtier drug simply to create a new drug, to have a molecule that is novel and therefore protectable by IP, or was it designed to be dirtier without thinking of it as being dirtier, but thinking of it as being sort of pluripotent across several kinases?
Yeah, so I obviously wasn't involved in designing this trial, so I can't answer that question as to what exactly their thought process was. I think it is true that RTB101 has a longer existing patent life than everolimus. So there is that component, certainly, to moving a drug through the approval process. And if you talk to Joan, she will tell you that they had unpublished data that RTB101 at the doses that they were using in this trial appears to be specific for mTOR complex 1, like rapamycin. So I think their thought process, in reality, it was probably twofold, right? Yep. The IP life was greater, and there's a biological rationale for testing RTB101 either alone or in combination with everolimus. And so that was really the design of the phase 2 trial, was one arm. It was structurally very similar to the first phase 2 trial, right? So you have older adults, same sort of age range. I think they had to be 65. They couldn't have a pre-existing age-related condition, significant age-related condition. And they had a control placebo arm, everolimus alone, RTB101 alone, and both. And I'll be honest with you, I don't remember the dosing on the RTB101. And so they looked at vaccine response, and then they also looked at, in this study, upper respiratory tract infections over the next season to look beyond just, if there's an impact of the mTOR inhibitor on immune function, is it specific to vaccines, or does it look like it's broadly boosting immune function? And again, I think you can look at the data and not be completely convinced, but certainly for the everolimus plus RTB101 and the RTB101 alone group, I think the everolimus alone group in this case didn't reach statistical significance, but for the combination and the RTB101 alone group, they saw improved vaccine response, and I think what was really striking was a lower risk of upper respiratory tract infection in the people who'd gotten the mTOR inhibitor over the next season. So that suggested that not only is it boosting vaccine response, but it's also broadly conferring protection against a variety of immune challenges in this older population. And again, very, very little in the way of adverse events, which gets back to the point, you hear people talk about how mTOR inhibitors, you could never use them for aging in people because the side effects are so bad. And it just gets frustrating over and over and over again to say, go read the data, go look at the data, right? That's just not true at the doses that have been tested so far. That's just blatantly false, right? There's no evidence actually for significant side effects from rapamycin monotherapy, everolimus monotherapy, or RTB101 at the doses that people are talking about using in this context.
Yeah, statins have far greater side effects than rapamycin.
I know.
And it's not even close. And I think statins are a very important type of drug, but to think how ubiquitous they are, and that we accept, hey, 10% of people. I think the literature says 5%, but really clinically, 10% of people have debilitating muscle aches from statins. That render it impossible to take them. Some people have elevated liver function tests that are otherwise unexplained. It is really frustrating for me to hear this, especially when people talk about how, well, we could never really study rapamycin because it's just too unsafe. It's like I'm not sure what data you're pointing to, but when you have it, let me know.
Yeah, I agree. So anyways, so that was the second phase 2 trial, which was successful. So then they went on to a phase 3 trial to hopefully get FDA approval for improving vaccine response and immune function in elderly people. And in that phase 3 trial, I'm trying to remember what they called that.
They think they called
trial.
it. I don't remember the trial, but now what was RAD001? What was that agent?
That's everolimus. That's the same.
That's what
drug.
they were calling everolimus. Right. Okay.
Yes.
Okay.
Yeah. They had a name for all clinical trials have names. So they had a name. I don't remember what it was. Yep. But in that phase 3 clinical trial, they only tested RTB101. So they took out the rapalog, everolimus, and only tested RTB101.
So there was no RAD001 plus RTB101. Okay.
That's right. No combination, no individual rapalog. That's right. And that clinical trial failed to hit the endpoint, and it was terminated halfway through. So this is my understanding. They were going to do one group in the fall season and one group in the spring season or something like that. And they got halfway through. They weren't hitting their endpoint, so they terminated the trial early. and then RTB101, or sorry, Restore Bio was the company that was doing this clinical trial to try to move RTB101 through to approval. The board basically merged them with a CAR T cell therapy cancer company, and they gave up on RTB101 because of the failed clinical trial. So, you know, why that clinical trial failed, I think still the data has not seen the light of day yet. I don't think I don't think it's come out yet. So we don't know for sure what happened. I think, you know, we can observe that the rapalog wasn't in there anymore, right? That is one difference between the two successful trials and the one that failed. And I believe Joan has talked about this publicly, that they also, in conversations with the FDA, were required to change the endpoint from laboratory confirmed infections, right? That was the endpoint, one of the endpoints in the phase 2 trial, to something else, which involved owner-reported thinking about dog trials here, patient-reported symptoms as the endpoint, and they didn't hit it. And so I think my understanding from talking to Joan is that data will come out at some point, and, you know, we'll be able to really take a look and see, you know, what the drug was doing and what it wasn't doing in that third clinical trial. My intuition is that it probably worked, and they probably got screwed by being forced to change the endpoint of that clinical trial. And if that's the case, then I think, you know, we really do need to have a conversation around the way that FDA, I mean, we need to have this conversation anyway, but the way that FDA is approaching clinical trials in the aging space, right? What needs to be shown for an appropriate endpoint, and what is the acceptable level of risk when the goal of the trial is to test whether or not an intervention is affecting a functional decline that goes along with aging or aging itself, right? And that's a bigger question. I certainly have plenty of thoughts around that. I know there are lots of people in the field who are thinking about this and working on it, and some have talked to FDA. It's a real challenge, and I think that, and I don't want to blame anything on FDA, right? I think that the people at FDA want to do their jobs to the best of their ability. I think there are constraints around the way that FDA is required to work, and the culture that does not, in my view, appropriately evaluate risk reward, right? I think that there is a culture of, you know, the risk has to be extremely low in people who are of normal health status for their age. I actually am trying very hard, I still slip, but I'm trying very hard not to use the word healthy when we talk about aging or older people. I'm relatively healthy for my age. I would say I'm probably in the top 10% health-wise for my age group. I am not as healthy as I was 20 years ago. We already talked about this, right? So I'm of, you know, normal to upper health status for my age, but I would not call a 65-year-old, a typical 65 or 70-year-old healthy. They're not. They're functionally impaired. And we really need, we being, you know, the regulators, society, policymakers, you know, really need, I think, to start taking a realistic look at what normal aging is, right? It is a progressive, chronic decline in function that at some point will lead to overt disease, and with 100% probability will lead to death, right? And so if we can intervene in that process to slow it down or reverse it, there should be some level of risk that is acceptable for that potential outcome. And I think that because we tend to think of 65, 70-year-olds as healthy as opposed to functionally impaired, it makes it really hard to have a rational discussion around what the appropriate level of risk is.
Matt, I think that is so astonishingly well said. And I've had so many discussions with Nir, and to a lesser extent, Steve Osted, about the choice of metformin over rapamycin in TAME. And it always comes back to this point, which is the regulators will absolutely, positively not consider rapamycin, which of course comes back to this question, which is what are we claiming to be studying and in whom?
Yeah.
The other thing is, the studies are being designed around disease, right? Progression of disease or outcomes of disease. So this really comes back to a broader theme, which is, where are we on the spectrum of understanding aging in the way that you're defining it and getting it further away from the discrete definition that involves a disease? Because until we really get people to center around that, your very eloquent explanation of there being no such thing as a healthy 70-year-old, until we realize that at the regulatory level, right, at the policy level, even at the scientific level, it's going to be very difficult to study the things that will have an opportunity to give step function changes in longevity.
Yeah. So let me start by pushing back on what you said about TAME and metformin versus rapamycin, because I think that's a myth that regulators would not allow you to do a clinical trial with rapamycin, right? We just talked about 3 clinical trials that were done, with mTOR inhibitors, 2 of which were with everolimus, right? Which is essentially rapamycin. So I think that is talked about as to why metformin was chosen for TAME. I don't think that is true, and I don't actually think that is the reason at all. I think that the
I've
FDA
pushed, by
regulators...
the way. I push. I needle near constantly about it.
Well, I mean, honestly, I think there are good reasons why metformin, makes sense to test in that context, and there's data in people that support that. So I'm not trying to say they should have used rapamycin.
Sure.
I think that people with expertise in the field can come to differing opinions as to what the best shot on goal is, I guess is the way I would put it.
You're just saying, let's say we picked rapamycin. Let's just say we picked metformin because of these reasons, but not because we thought that rapa wouldn't be safe enough, or the regulators themselves would decline it.
Yeah, I think they'd let you do the trial. Obviously, they would pay attention to adverse events, and there would be concerns around adverse events, but they would certainly let you do the trial, and that's been proven, right? I mean, Restore Bio did the trial, right? And it wasn't because of adverse events that it got shut down. I think that's the other important point to make. I think the regulators at FDA are doing the best job that they can within the constraints of how they are required to regulate drugs. I have a real problem with the way we regulate drugs in this country, but I don't necessarily blame it on the people at FDA. But I do think if you came to them with a clinical trial where you had an endpoint that was quantitative and functional and related to quality of life in people, they would let you do that clinical trial with rapamycin. I'm 100% certain of that. The challenge is, I think the reason why this hasn't happened, 1, rapamycin's off patent. Nobody's going to make money off of it. And 2, there is a misplaced concern about side effects, which we've already talked about. It's just not reality that the risk is significant at doses of rapamycin that would be tested. So I think the real challenge, though, is identifying the right endpoints for a clinical trial in aging. You're not going to do lifespan in people. We can do it in dogs. You're not going to do it in people. I think we just have to accept that. So what is the right, or what is, I don't even want to say the right approach, because I don't think there's one, but what are some approaches that one might consider if your goal is to move FDA towards approving a drug in people of normal health status to prevent age-related functional declines in disease, right? To target aging. That's what I mean when I say prevent age-related functional declines in disease, to target aging. So if your goal is to get there, so what does that clinical trial look like? So the TAME trial is a specific example of one strategy, which is to take people who already have one age-related disease and ask whether your intervention, metformin in this case, can delay the onset of the second age-related disease. It's a comorbidity trial. That makes a lot of sense because we know with pretty good precision how long that time frame is on average, from the first age-related disease to the second age-related disease. And so you can quantitatively assess, does your intervention increase that length of time? That's the rationale behind TAME. In my personal view, the limitation of that approach is it's not a true healthy aging study, right? It's not taking people who are of normal health status for their age and asking whether the intervention can improve or extend the healthy period of life, right? So it's a different design, but I totally get why TAME was designed that way, and I like the design. I think there's a reasonable chance it'll work, but it's different from the way I would think about a clinical trial in this space. What I would do is I would try to identify the best single endpoint or set of endpoints that correspond to a significant functional deficit that impacts quality of life in older people, and assess whether or not my intervention improves that. And optimally, that endpoint would have quantitative markers that you could measure, right, to show that you've improved it. So Restore Bio went with immune function, and they went with vaccine response initially, and then ultimately, I think in the phase 3 trial, they were also looking at respiratory tract infections, right, over the next season. That was their endpoint. It's quantitative. The problem is it's really hard, right? It's a really noisy endpoint. And I'm not at all criticizing them. In fact, I think, as you know, Joan Manick is one of my favorite people. She's a good friend. I have an amazing amount of respect for her. I think they went for it, and for reasons that were probably beyond their control, that clinical trial failed. But I have so much respect for what they tried to do. I'm just saying it's a tough clinical trial. It's a tough endpoint. It's noisy. I think there are other endpoints that you could consider that that might not be as noisy, right? That you could consider doing a clinical trial for. So one of my favorites at this moment is periodontal disease, and that's because my lab has published that aged mice get periodontal disease, that 8 weeks of treatment with rapamycin reverses the clinically defining features of periodontal disease in mice. We know that something like 2/3 of older adults have periodontal disease or will get it, and those who have periodontal disease are at higher risk for dementia, cardiovascular disease, diabetes. So it's connected in some way to other age-related diseases.
And by the way, a recent podcast of mine explored this topic, and it may in fact be causally related through that inflammatory axis, right? I mean, I think that's probably the strongest line of evidence connecting oral disease with systemic disease. It's through this immune inflammatory pathway. So I think that's actually an elegant approach.
So the reason why I like periodontal disease, right, is the endpoints are extremely quantitative, right? So what we looked at in the mice are gingival inflammation, bone around the teeth, which can be measured, crudely by pocket depth, more quantitatively by X-ray, and microbiome. That's really at least in my understanding. I'm not a dentist, but I've learned a lot about oral health over the last few years. That's my understanding of, if you have gingival inflammation, you've lost enough bone around the teeth, you don't even have to have the dysregulation of the oral microbiome, but it always goes along with it. You've got periodontal disease, right? So there are nice quantitative endpoints that can be looked at in people, and it's extremely non-invasive, right? The way that you do this clinical trial is you have people come in for a dental exam, right? Before and after treatment. So you've got a shot at seeing changes in quantitative endpoints that we can not just delay, but actually reverse the declines in mice in people, in a reasonable time frame. So you could easily imagine something similar to the structure of the Restore Bio trial with rapamycin or everolimus or RTB101 or pick your favorite intervention, where you treat people for 8 weeks, 3 months. They have a dental exam before, a dental exam after, a dental exam 6 months later, and you just look and see what was the impact of the intervention. So it's a pretty straightforward clinical trial, and I think I hope we will get this off the ground. We're actually trying to get some funding to do a clinical trial now. This is I should say
in humans or in dogs?
In people, yeah,
okay.
In people. And this is really the person who deserves all the credit for this crystallizing in my mind is a gentleman named Jonathan Ahn, who was a DDS PhD student. So he had already got his dental degree. He did his PhD with me, and he, before he came to my lab, he came to me one day. I vividly remember this conversation because I had never thought about oral health. And he goes, people get periodontal disease when they get older in much the same way that people get Alzheimer's disease or heart disease. If you look at the risk profile as a function of age, it looks strikingly similar to these other age-related diseases. what do you think maybe the biology of aging is contributing? And, in hindsight, it's like, oh yeah, that makes a lot of sense. But I had never thought about that before. And so he came to my lab and showed that we could do this in mice. We could see age-related periodontal disease. We could see bone loss around the teeth. We could see inflammation of the gums, and that we could reverse that with rapamycin. And so he's actually now a faculty member at the University of Washington, and he's really the one who's trying to push this clinical trial forward. So I'm sort of peripherally involved, but John is really the guy in this space. He's going to be a rock star.
And this would be a phase 2?
Yes, right.
What's the approximate budget for this study?
I mean, we're just submitting the grant now, so I don't know. It's very early, right?
What would be the budget for this study?
So it's going to be a 3-year grant. I don't know. I think it's R01 size, couple $100,000 a year over 3 years.
Okay. If money were no object, what secondary endpoints would you add to that study? In other words, if you could power this study to hit that as your primary, but also go after multiple secondaries, let's just throw in immune function. There'd be no reason not to repeat what was done with RAD001. What else would you add to that?
Right. So if you look at the mouse data, I mean, I think the mouse data is it's a reasonable place to start. Again, obviously mice aren't people, but it's a reasonable place to start. So where does rapamycin reverse functional declines associated with aging?
Hearing, right? Wasn't there that study that just came out? Yeah, it just came out 2 weeks ago.
Absolutely.
It reversed age-related hearing loss, which that got me very excited.
Yeah, I agree. So that's again a very easy and quantitative endpoint, right? Wouldn't it be amazing if you could improve age-related hearing loss with rapamycin? And so that's a no-brainer. Immune function, I mean, I agree. If money was no option, sure. But even in the context of a so let's say the periodontal disease clinical trial that I talked about, if you could also measure hearing in that clinical trial, right? It's a big bang for the buck, right? It costs you almost nothing, and you get potentially another endpoint that you could hit on. Where else? So muscle function, there's pretty good evidence that at least rapamycin can prevent sarcopenia. I don't think there's a lot of data yet on improvements in muscle function, but you could do things like, grip strength, walk speed, things like that. Cognitive function, that's hard. Again, I put that in the sort of the same category as immune function as an endpoint. It's a tough endpoint, but it would certainly be interesting to look at cognitive function in this elderly population of normal health status. So some of these people are going to be on the road to dementia. They won't have dementia yet because that's an entrance criteria to get into the trial. Heart function is another place where we see reversal of age-related declines. This would be hard. So this is a different clinical trial, but also potentially cool. Reproductive function. You wouldn't do that in that same patient population, probably. Yeah. But in mice, there's pretty good evidence that you can reverse, at least in females, reproductive declines that go along with aging, or at least delay them.
Let's just pause on that for a second, Matt. That is staggering when you consider where we are today from a standpoint of reproductive medicine, right?
Yep.
Women are having children later and later. And I can't tell you the number of just patients in my practice, either male or female, for whom this isn't a top of mind priority. It's simply unbelievable. And to think that there would be I never really had thought of this, honestly, because I don't think I've paid attention to that subset of the rapamycin literature. If you were to, and again, this is guessing, but how much of an impact do you think you could have? So if you had a woman who was 40 years old, who's been, she's obviously still premenopausal, but her AMH is low, and or it's reasonable, but she's got significant aneuploidy. For the listener, meaning whenever her eggs are produced, they don't evenly divide into the right number of chromosomes. So they don't show up with one of each chromosome. And that's an enormous cause of infertility as a woman ages, is this aneuploidy. So they either omit a chromosome or include two, and those almost universally lead to an early miscarriage. Some of them, like trisomy 13 or 21, will make it. Do you have a sense of what type of magnitude of an effect this could have?
I think the honest answer is no. So I think there's a couple things to say on this. One is there's not a lot. There have been, I think, 2 or 3 studies in mice looking at this, right? And so there's not a lot of data on magnitude of effect, even in mice. So my guess is that in people, so I don't even want to comment on magnitude of effects. I really don't know. I think the way that you would design a clinical trial, though, would be very similar to what we've talked about with rapamycin already, with the immune function or periodontal disease. You would take, a woman premenopausal, let's say early 40s, a group of women, and do 8 weeks of treatment, right? And then a washout. And then you could look at your endpoints, or if they are going through IVF, for example, right? Look and see whether or not you get an improvement in outcome using that functional measure. Why
the 8 weeks? Do we really believe that would be a sufficient amount of time? I mean, are we just coming up with 8 weeks because that's where we saw the vaccine response in the everolimus trial? Or do we think if you were shooting for the moon and cost were not an issue, what would be the downside of longer treatment?
Well, a couple things, right? So one is increased risk of side effects, right? I mean, I think that's one. The longer you go with any treatment, the more risk there is for an adverse event, even though I think the risks are pretty low. And the other is, I think, so with here's a really interesting piece of data that we don't have with the immune function studies in mice or people. In all of those studies, the treatment was stopped.
That's right.
And then there was a 2-week or so period before the vaccine was given.
So what was the rationale for that washout?
I think it's because people think and thought about rapamycin as an immune suppressant, right? So that you might, and this is where I was going with that. What we don't know is if they were still taking the drug, would you have gotten the same effects for immune function? I don't know. So it's an important question that I think we just don't know the answer to. But the other risk is that at least for some of your functional measures, if it requires, let's say, hyperactivation of mTOR to get the response, you might impair that by doing continued treatment with rapamycin. And at least all of the data that I've seen, limited in people, extensive in mice, 8 weeks is enough to give you essentially that full benefit for whatever the functional output is that you're looking at. Maybe not for lifespan, right? Maybe multiple 8-week, transient interventions would be better than one. Only thing that I know of for data there is our study where we did 3 months, right, of rapamycin treatment between 20 and 23 months of age, and then let them go to the end of life. The magnitude of effect was pretty similar to what the ITP saw. So it was reasonably close to continuing treatment, but we don't know.
But 8 weeks in mice is, what would that be in humans, right?
Yeah, I know where you're going with that, right? If you were to linearly extrapolate that would be a few years, right, in people. Yeah. And I agree with that. I think that the immune trials that we've talked about suggest that might be long enough. But I agree. We don't know is the answer. I'll just say, so I haven't talked about, my experience with rapamycin, and I really don't talk about this publicly, but I'll do it here. So I've tried 8 to 10 week courses of rapamycin a couple of times. The most recent time, it was because this was probably spring of 2019. So I'm pretty active. I play softball in the spring. And I noticed I had a lot of shoulder pain. And by the end of the season, it was to the point where I couldn't throw a football. Like I couldn't go play catch with my son. Actually, that's one of the hardest personal sort of aging experiences I had was when we went across the street to the park and I was gonna play catch with my son, and I couldn't do it because my shoulder hurt so much. It was my right shoulder. And I thought I must have a rotator cuff tear. I went in to see the specialist, finally got diagnosed with frozen shoulder, which is inflammation of the shoulder capsule, which happens to some people as they get older. Extremely painful, completely limited my range of motion. And the doctor was like, well, I could give you a shot of cortisol, but I don't really recommend it. That can degrade the cartilage. Really, there's not a lot you can do. Some people, it goes away after a year. Some people you just learn to live with it. And I was pretty depressed by that diagnosis, right? I was like, at least if it was a rotator cuff tear, I could get surgery, get it fixed. So I go home and I'm sitting there and I'm thinking, so I'm looking on the internet and I see, okay, it's an inflammation of the shoulder capsule. I'm thinking to myself, what do I know that has anti-inflammatory effects, in the context of aging, right? Rapamycin. So I got some rapamycin and I did 8 weeks. And I mean, again, placebo effect is real, but this was so painful. I don't believe it was placebo effect. Within 2 weeks, I had probably half my range of motion back. Within 8 weeks, I was back 95%.
And were you just dosing once a week?
Once a week, 8 mgs once a week. Yeah. I mean, I couldn't do this 2 years ago, right? Because it hurt so much, right? And now it doesn't hurt at all. Within 8 weeks, and I want to be careful because I want to say I'm not encouraging other people to go do this, but I am a true believer after that experience, right? I don't think it's placebo effect. I don't see how it could be with how painful it was, how real the limitations were on range of motion. So that goes to this 8-week question. At least for that indication, which I believe this was a real effect, 8 weeks was plenty. And it hasn't come back, right? Which actually kind of makes sense with frozen shoulder. I think when people recover from it, it doesn't always come back. So I think that, again, a lot of these age-related conditions that are inflammatory driven, you can kind of reset that with an 8-week treatment. And rapamycin, I suspect senolytics, if we had good senolytics, would do pretty much the same thing.
Do you think that rapamycin is itself a senolytic?
I don't think it's a senolytic in the sense that it at least the classical way people have thought about senolytics, where it kills the senescent cells.
Right.
I absolutely think it turns down the chronic inflammatory signaling that is driven by P16, P21, NF-kappa B. Yes, we see that in mice, multiple tissues, no question about it. I also, I still think the senescence field is a little bit messy in the terminology. I think a lot of what people call senescence isn't truly being derived from senescent cells the way that we think about them. It's P16, P21 mediated inflammatory cytokines, right? Doesn't necessarily have to come from senescent cells. No question, rapamycin shuts that off, and it shuts it off within 8 weeks, at least in mice, in a lot of tissues.
And do you think it's doing that independent of what it's doing at the mTOR, or do you think that it's doing that through mTOR?
I would be shocked if it's not doing that through mTOR. I don't know of any good evidence that rapamycin has off-target effects that aren't through mTOR.
Yeah, okay. And so really it's these SASPs getting whacked that is how it would act through via the senescent pathway, as opposed to targeting a senescent cell directly. But that's, by the way, that's been my reading of the literature. Would you agree with that?
Yeah,
it's really.
I think that's right.
Yeah.
I think in some way it shuts off those chronic inflammatory signals.
The secretories, yeah.
Yeah. Yeah, and maybe other stuff, right? I mean, we always look at the SASP because that's what we know. I mean, I think, this is natural in science. We look under the lamppost. We measure what we know to measure, right? It would not shock me at all if there are other things that go along with the canonical SASP, that senolytics or rapamycin or caloric restriction. I think that's a big part of fasting. Fasting does the same thing, right? Tamps down on that chronic inflammatory signaling, maybe through mTOR, maybe through other mechanisms. So I think that, what we know about is part of it. It wouldn't shock me if there were things we don't know about yet that also are contributing. Yeah. But getting back to this 8-week, right? That's how we got started. Yeah. So I tend to think, based on my personal experience and the little bit of data from these 2 clinical trials, that's probably long enough for at least some endpoints that are driven primarily by immune dysregulation and chronic inflammation.
Yeah, I think 2.5 years ago when I started, I was very strict about 8 on, 6 off, 8 on, 6 off, 8 on, 6 off. And I don't know, a little while ago, I just sort of said, yeah, I'm just not coming off. And I wish I had a biomarker to point to. I wish I had some way of measuring whether this is the right thing to do, or if 8-4, 8-4, 8-4.
Right.
There's a symmetry to 8-5 because you'll get through exactly 4 cycles a year. Maybe I do 8-5, 8-5, 8-5, 8-5. But it really frustrates me that we don't have a biomarker for this.
Yeah, or aging in general. Yeah,
or for aging in general. So let's talk a little bit about that. So what does that look like? I mean, when I had Eileen White on the podcast, it's been maybe 1.5 years now, we had a really interesting discussion about why we don't even have biomarkers for autophagy. I mean, something that is so important, and we can't measure it. And this was important in the context of people who choose to calorically restrict or fast.
Right.
You know, is fasting for a day long enough to generate a meaningful amount of autophagy in a human? In a mouse, it clearly is, but in a human, is it? No idea. Is 2 days, 3 days, 7 days? 7 days is almost assuredly enough. There's a big difference between fasting for a day and fasting for 7 days.
Yeah.
Why don't we have biomarkers for that? Why don't we have a biomarker that can assess nutrient sensing better? Why don't we have you could argue we have some biomarkers. We can measure telomere length, but my feelings on this, Matt. I'm in the camp that thinks measuring telomere length is not helpful at all for aging. And I think there's plenty of data to suggest that while telomere length is a very important marker of cellular division, it really speaks very little about the organism's state of aging, despite the popularity of that biomarker.
Right.
Even the epigenetic clocks, I don't find to be helpful. I find them to be far too, and I'd like you to push back on this if you feel as much, but I've seen how easily they can be manipulated by short-term interventions that don't seem biologically relevant.
Yeah. So I think I'll start with the epigenetic clock, because everybody, that's a big,
let's explain to people what that is. Let's start from the beginning. Assume people don't know what an epigenetic clock is.
Right. So the epigenetic clock refers to typically chemical marks on DNA that regulate gene expression, whether or not, the gene that is located at specific points in your genome gets turned on or off. And what has been observed is that those marks change with age in pretty much every organism where it's been studied, and that you can identify patterns of change at specific locations in the genome, so specific changes in these chemical marks with age that correlate very strongly with chronological age. And so that has led to the idea that you can create clocks that look at specific changes in chemical marks in the DNA, the genome, that are telling you something about how long that organism has been alive. And then what sort of has emerged from that is that there are two things that have emerged from that. One is you may be able to use that chronological aging clock to find individuals whose marks don't fall on the line that you would expect it to fall on based on their chronological age. In other words, they have marks that make them look older or younger than their chronological age says that they are. And so you would hypothesize that those individuals biologically, if those marks are really reflecting biological age, might be aging more slowly or more quickly. And what's been shown is that indeed, those individuals who tend to be off the line, depending on whether they seem to be aging more slowly or more quickly, are at lower or higher risk for specific diseases. So that adds some level of confidence that this epigenetic clock, chronological epigenetic aging clock, is actually reflecting biological age. And so the idea is maybe we can use that information to develop epigenetic clocks that will, in a predictive way, tell you how old you are biologically, right? So you can get tests now. There are plenty of companies now that are selling these things where you can go buy your epigenetic blood test. Mostly this has been done in blood cells. That's one limitation to think about, is almost all of the literature in humans is developed on epigenetic clocks from blood. And it's still, I think, a little bit of a question, even if this is reflecting biological age, it's the biological age of your blood, which may or may not reflect the biological age of your entire body. But you can buy tests now that based on you give them some of your blood, they will tell you your epigenetic biological age or some number.
So they're looking at PBMC, I assume?
I don't know, honestly. I'm not involved in any of this stuff. So I don't know exactly what. Yes, most of the studies that have been published are PBMCs. I don't even, they may even have saliva tests now. I don't know, honestly, how these commercial companies are doing it.
I mean, some of the clocks I've seen where I've just immediately discounted them is when some of their inputs are things like glucose level, vitamin D level, which are things that vary so much from day to day. And by the way, are so easy to manipulate. Like you can take a vitamin D supplement or not take a vitamin D supplement. You can, have a high cortisol spike one morning and your glucose is 110 versus have a good sleep the night before and your glucose is 95. So something that's that malleable, I just don't think makes sense as an ironclad marker of true, biologic age.
Yeah. So let me take a step back. So the epigenetic clocks, right, are probably the one that people talk about the most and have gotten the most traction in the field. And I guess I'm a little bit of a skeptic, but I mean, I believe these clocks, I believe the data, and I believe that that the correlations are extremely strong. I'm a little bit worried still that there are so many data points in the epigenome that you can find a pattern that will fit anything you go looking for. And that, so I'm a little bit worried about the dimensionality of the data and whether or not, it's pattern matching in some cases, rather than it's really truly going to be a robust predictor of biological age. That probably reflects what is admittedly, my limited understanding of the mathematics behind a lot of the epigenetic clocks that have been built. So I don't view that as a strong criticism. It's just a personal sort of concern that I have.
So you're basically saying without doing the complex mathematics to correct for the multiple looks that you can take at the data, you could be tricked. And I have not spent enough time looking at that either. I would like to have Steve Horvath on the podcast at some point, because I think Steve could speak to that probably better than anyone else.
He's the expert,
yeah,
for sure.
So that's.
But the other point I wanted to make is what you alluded to is now what people are doing is going beyond the epigenetic clocks to try to look at every possible thing you could measure, sometimes combining that with the epigenetic clock to build these super clocks or multi-clocks or multi-omic clocks, right? And I think there's huge power in that. But it also increases that dimensionality problem that I just mentioned, because, all of a sudden now you've got, if you're doing omics stuff, you've got tens of thousands of additional data points that you can measure, and you can fit a pattern where a lot of this, and I think even Steve and other people who are in the epigenetic clock field would agree with this, where a lot of this has yet to really mature is in getting us to biological explanations for what the patterns are telling us, right? Mm-hmm. What genes are they that these marks are located at, and are those in any way causal for biological aging? So I think if you get to the point where you can understand mechanism, it's going to be much more powerful. I also think, though, this gets to the fundamental challenge with biomarkers, and I think this is where you're dissatisfied. We have a lot of biomarkers of aging. We just don't have any validated biomarkers of aging, right? And it's a real, this has been a problem, since I was a graduate student. Everybody's wanted biomarkers of aging. The NIA had a huge program where they did all this funding to identify biomarkers of aging. I think it was back in the 80s, right. Maybe before my time, 90s maybe. You can identify all sorts of things that correlate with age. How do you get to the point of convincing yourself first and other people second that these things are actually telling you something about biological aging that can then be used to understand whether an intervention is working, first of all, at the population level, but ultimately where we want to get to is at the individual level, right? So what we all want is a test that you can take and you can fast. You can do your fasting regimen, you can do your rapamycin, you can take metformin, whatever, and you can come back and find out, is it working from this set of biomarkers? And that's where we want to get to, and we're not there yet. I think everyone would agree. I'm not sure when we're going to get there.
So who's the natural owner of getting there? Because, I had this discussion with Steve Osted recently, and he made the same point you did, which is, look, the NIA tried to do this a long time ago and tried, validly, right? They put a lot of money into it. You could make the case that the technology simply wasn't mature enough to do this. 30 years later, we have a lot more tools at our disposal, right? You've got the entire world of omics at your disposal, plus you've got machine learning, plus. Is there any reason this couldn't be done today? And if so, this strikes me as a project that's almost too big for academics, right? Because it's too disjointed. But at the same time, it's not a particularly interesting commercial problem to solve, because it's far too big an investment before you could get to why you would care about it, right? A commercial problem is, give me a drug.
Yeah.
But I'm arguing you can't develop a drug really well without this. So there's a bit of a cart and a horse thing, which is someone's got to pony up a lot of money to develop the foundation of a pyramid that will ultimately become a great tool for drug discovery and a much more streamlined manner in which we could do clinical trials around this.
Yeah. So I think the answer to your question is it depends on whether you're talking about doing this preclinically or clinically, right? I actually think this is a
Don't you think it has to be done both?
Well, eventually, yes. It's a problem that can be solved today preclinically. Like there is no real barrier to doing what you just said. So multi-omic analysis of aging in mice with interventions, applying machine learning to identify patterns that predict the effect of interventions and individual outcomes for longevity. You obviously have to think a little bit about, what can you measure? If you want to do this longitudinally, right, you can't kill the animals, right? So you're sort of restricted to blood, but so there are some practical aspects, but there's no technical barrier to doing that now. Who should do it? Who might be doing it, right? I think this would fall maybe in the realm of what Calico could do, right? They've got the resources, they've got the expertise.
Is there any evidence that Calico is interested in this type of a problem?
I think so. I don't know. I honestly don't know anything about the inner workings of Calico these days. I think conceptually they are interested in multi-omic signatures of different aging processes. I don't know if they've done this particular experiment. They certainly have the resources and expertise to do it. They're not the only ones, but they're the first ones who come to mind. And they sort of fit this space between true academia and industry, right? Yeah. Where they're kind of this interesting beast in the middle. So I think it could be done preclinically, and you could actually then, let's just say you have this test, right? You get to the end of day, you say, okay, these are the most predictive, 24 things that give you, 95% confidence on remaining life, right? Or whatever your endpoint is. Then you get that test, and then you show whether it works or not in an independent study. And if it does, I'd be pretty convinced, right? If you can show me that you create this test and then you go do a separate experiment and you can predict when the mice are 6 months old, how long they're going to live at an individual level, I'm impressed. And if you can show that this intervention, when you treat them, makes the signature go in the way that you think it should go, and you can predict they're going to live 30% longer, I'm even more impressed. I'll believe it at that point. So that's not easy, but I think it's doable. I think we know enough now, and we've got enough things that we could measure that you could certainly build the test, and then whether it would work in the validation step or not, I don't know, but I think you could probably get it to work. You can't take exactly that same approach to people. And this gets back to that the same issue that we talked about with clinical trials, right? It takes a long time to do the validation step and know that you have actually changed somebody's biological state so that as they get older, they are at lower risk for disease and are likely to live some X% longer. So you're almost obligated to have some level, you have to have some level of faith in the test at that point, right? And I don't know, it's going to be different for everybody. And I honestly don't know what the regulatory step has to be, right? Before you could convince regulators that you can actually, go out and tell the general public that this test works. Although I will say there are already people doing that, and the regulators aren't doing anything about it as far as I can tell. So, there you are.
Let's come back to your dogs. We spoke about them at length 3 years ago when we sat down to talk about rapamycin. But again, let's assume a clean slate, and folks might not be familiar with some of your work specifically around dogs and how working with companion dogs offers many advantages over working in mice, beginning with some of the obvious, like they're far more genetically similar to us. They live in our environment. And, they also seem to die of things that more closely replicate how we die. They die of heart failure. They die of cancer, but not the same type of cancer that a mouse gets that's almost genetically predetermined.
Yeah. So just to start from ground zero, we at the University of Washington and Texas A&M and at several other institutions have a large project called the Dog Aging Project. And so the goal of the Dog Aging Project is really to understand the biology of aging in companion dogs or pet dogs. Some people, when I say companions, some people think I mean, like
seeing eye dogs,
or things like that. Yeah, no, but it's pet dogs. And there are really two aspects of this project. One is a large-scale longitudinal study of aging, completely observational. The goal there is really just to understand what are the most important genetic and environmental factors that influence healthy aging in dogs. And part of that, this is getting back to the conversation we just had, is to measure as much as we can about those dogs every year as they go through their lives, in order to be able to identify patterns, right, that are associated with health outcomes during aging, lifespan, disease incidence. So in some respects, it's a similar approach as to what you would do if you wanted to create biomarkers of aging, right? So that's the longitudinal study of aging. The second goal, and so one way to think about that is that's to try to understand aging in dogs. The second goal, and this is really where I'm focused largely, is to do something about it. So can we slow or reverse biological aging in pet dogs to increase healthy lifespan? And so that ultimately, I hope, will be a series of veterinary clinical trials to test interventions to figure out, can we slow aging, reduce disease, and increase lifespan in pet dogs? The first clinical trial is with rapamycin. And so that's our first shot on goal, but I hope it won't be the only one. And so you talked about, so why dogs? Why pet dogs in particular? And I think you hit on, most of the most important reasons, right? So they've got this really interesting and powerful genetic architecture. We have a couple hundred purebred breeds of dogs, which you can almost think of as inbred strains, right? And then on top of that, we have this mixed breed population. And that's coupled with phenotypic diversity. So for almost any trait that you think about, dogs are more diverse than people are even. Body size is a really easy one. Everybody can just think about the difference between a Great Dane and a Chihuahua. So that combination of unique genetic architecture with phenotypic diversity is really powerful for mapping genotype onto specific traits. And lifespan is another case where you have this strong diversity, right? A Great Dane will grow old and die, maybe in 8 to 10 years, whereas a Chihuahua often will live to be 16, 17 years old. So, we're talking 100% difference in lifespan. So that's really powerful for mapping genotype onto lifespan. Dogs share the human environment is another big one, right? And that's for me one of the most important, because we cannot model that in the laboratory. In fact, we do exactly the opposite. We really try to limit variation in environment to extreme measures. Dogs share our environment, with the exception of diet, share almost all aspects of the human environment. And so that's a bridge in some ways between laboratory studies and human studies. And as I've already alluded to, they age more rapidly than we do. Their lifespan is substantially shorter. We all are familiar with the idea of 1 human year is about 7 dog years, right? That's just another way of saying dogs age about 7 times faster than people do. And we can talk about that. It's interesting. If you actually look at the epigenetic clock, it's not a linear 7-time rate, but I think it's close enough, right? It's close enough. And as you suggested, they age very similarly to the way that people do. They get essentially all of the same age-related diseases, and they're all age-related. And they show the same functional declines that people do. So dogs get arthritis as they get older, right? And arthritis is, I guess it's a disease, but it also starts as a functional decline, right? Anybody who's ever had an old dog, you will notice that your old dog doesn't move around as much, doesn't walk as fast, right? So they are going through the same changes with aging at the functional level that we are. Again, it just happens 7 to 10 times more quickly. So they're a very powerful animal in which to understand aging and test interventions for that reason. And you can do it in a time frame that's feasible. That's, again, I think, we've talked about the challenges with doing a clinical trial for lifespan in people. Even if we believe metformin is going to extend lifespan in people, you're not going to do a clinical trial to prove that. You can do that clinical trial in dogs. And so we've designed the rapamycin, the test of rapamycin in aging dogs, or triad. That's what we call our clinical trial. We've designed triad so that we'll be powered, statistically powered, to detect a 15% change in lifespan within a 3-year window, right? So we can do a 3-year clinical trial, reasonable cohort sizes to see an effect on lifespan that's comparable to what rapamycin does in mice.
That's a pretty high bar, Matt. That's, are you at all worried you've underpowered that, given that you only have, and they're being administered the drug for the entire 3 years?
No. So yes, yes, I'm worried that the study is underpowered. I will say, from my experience now, we've done 2 safety clinical trials, and this is our big clinical trial. So this is my 3rd veterinary clinical trial. I've learned that there are many reasons to be concerned when you do a clinical trial. Clinical trials are a lot of guesswork. You have to take an educated guess about a lot of different things. You can't test every dose. You can't test every duration. You can't test, an infinite number of study subjects. So I'm worried about this clinical trial for many reasons. I think we've done the best that we can, given what we know and given the constraints that we have to work under, to give ourselves a reasonable shot. 15% might be a high bar, but it's consistent with the lower end of what people see in mice. So the first study at the low dose of rapamycin in mice from the ITP had a 14% effect, I think, in females and a 9% effect in males. Subsequent studies at higher doses had larger effects. So,
do you expect to see a sex difference in dogs?
I don't know. So people still don't completely understand why female mice seems to respond to a given dose of rapamycin better than male mice. So it's correlated with blood levels. So I think the simple idea is that male mice either take up rapamycin less effectively or break it down more quickly. There's no evidence for that in dogs. We will be measuring rapamycin levels in the dogs, so we will see if there is a difference in blood concentration in females versus males. From the limited data that we've got so far, we don't have any evidence that that's the case in dogs. And I don't know of any evidence in people that that's the case either. So that might be a mouse-specific thing. I think there's this misperception that rapamycin, works better in female mice than in male mice. That's not true. At a given dose, especially
at a given
the lower
plasma
doses,
dose, we don't know if it's true, right?
No, given dose in the food,
yeah.
At lower doses, females show a bigger lifespan extension. When you go to higher doses, the males catch up. And if you push it too far, you can actually find a dose where female mice, the lifespan extension starts to go back the other direction, and male mice actually get a bigger lifespan extension. So I think it's more about effective concentration than it is a male versus female truly sex-specific response.
And in the dogs, you give it daily in their food?
No. So it's once a week.
Okay.
So this is a now guesswork, right?
Now
What's
we're
the best
back
way to
into
do
the
it?
alchemy.
Yeah.
Yeah.
So we've tested 3 times a week and once a week, and we decided to go with once a week for triad, and it's a guess.
And how many mgs per kg are they getting? Is it 1 dose?
0.15 mg per kg once a week. And that was based on our observations from 0.05 mg per kg 3 times a week.
Yeah.
That's how we get, 0.05 times 3.
So let's talk about what might be going on in the ITPs, which I've had Rich Miller
Peter,
on.
let me just come back first to the dog study, because I want to make another point, which is that you asked if I was concerned about being underpowered for a 15% lifespan effect. So lifespan is our primary endpoint, right? Which is important, because I think this is the first clinical trial that has lifespan, in a healthy or normal health status population as the endpoint. I will say it's funny because I get pushback from clinical people. You can't call this a clinical trial. It's in dogs. It's not in people. And I just simply respond that a veterinary clinic is a clinic. It's a veterinary clinical trial, but it is a clinical trial. And I think this is the first clinical trial with lifespan as the endpoint. I don't know if you can hear my dog. You want me to stop until he stops barking?
No, it's funny. It's totally appropriate that as we're talking about dogs, we can hear your dog.
The environment. So the point I want to make, though, is that lifespan is our primary endpoint, but we are tracking multiple secondary endpoints to give us a picture of, is rapamycin broadly impacting the aging process? So we're looking every 6 months, the dogs get echocardiograms to look at heart function. The dogs will be fitted with activity monitors periodically to look at spontaneous activity. Every 6 months, the dogs will get cognitive assessments to look at cognitive function. We're getting blood chemistry, serum metabolome, fecal microbiome, and of course, we'll be tracking disease incidence as these dogs get older. So, over this 3-year window, I hope that even if we don't see that magnitude of lifespan extension and we don't reach statistical significance, if there is a broad effect on multiple age-related outcomes, that we will be able to detect changes in other secondary endpoints.
What's the sample size? You're going to have 2 groups, placebo versus dose?
Right, half placebo, half treatment. The intention is to randomize 350 dogs equally split between the 2 groups, so 175 of each.
And do you know roughly, if you had gone with a 10% effect size, how many that would have required? How many more?
I don't recall off the top of my head. I think probably around 500.
Yeah. In your previous work, you had already got a sense of what was happening in animals with heart failure. What remind people a little bit about that if they don't remember the first episode?
Sure. So there's really good data, at least 3, maybe 4 now, studies from different labs in mice showing that if you look at age-related declines in heart function, particularly left ventricular function, so the several measures of left ventricular function decline with age, that 8 to 10 weeks of rapamycin is enough to reverse those changes and make the young heart, by echocardiography, look functionally make the old heart look like a young heart. There's also data in mouse models of a few different types of heart failure. So dilated cardiomyopathy is work that we've done in particular, where you can reverse dilated cardiomyopathy in mice with rapamycin treatment. So I think there's really strong evidence in mice. In our first clinical trial, it was designed to really only be a safety trial. There were 24 dogs. 16 got rapamycin, 8 got the placebo, but we had the dogs also get echocardiograms before and after the treatment period. And in that study, there were statistically significant improvements in 2 of the 3 measures of left ventricular function by echocardiography in the dogs that got rapamycin compared to the placebo. What was, I think, to me, most interesting in that data was that the improvements that we saw were exclusively found in the dogs that came in with lower function. Now, one thing to note is none of these dogs had function so low that it would be clinically diagnosed as heart failure, right? So it was normal age-related declines in function, and it was exclusively the dogs with the lowest function that showed the improvements from rapamycin. That is an interesting observation, which my gut feeling is real. Again, a small cohort, so I don't want to make it out to be stronger than it is, but it also is intuitive, right? We know that individuals have individual trajectories of aging and develop a unique spectrum of functional declines. And it makes sense that some of these interventions that are restoring function would primarily be effective in people who've lost function. That's just intuitive. But so I think that's probably what we'll see, in our long-term study in Triad, where we follow the dogs for 3 years, is that there's going to be variation at baseline, and it might be the case that those individuals that had the lowest function at baseline are the ones that are going to see the biggest benefit, if there is a benefit at all.
Now, in Triad, will you be trying to create somewhat of a homogeneous sample in size? By that, I mean the size of the dogs, or are you going to be completely heterogeneous with respect to the size of the animal? And also, what is the age of the animal? What are the exclusion criteria around the age on either end, low or high?
Right. So age, they have to be at least 7 years old to come into the study, so they have to be middle-aged. And we do have a size range. So the dogs have to be between 40 and 100 pounds to be randomized into the study.
So it's not for little dogs.
That's right. And the reason for that is not because we have any reason to think rapamycin will work differently or better or worse in little dogs. It's because big dogs age faster than small dogs. Let me come back to that in a minute, because that might not be that might be an oversimplification, but they certainly live shorter than small dogs and develop many age-related diseases and functional declines at an accelerated rate compared to small dogs. So we need a population, that's already middle-aged and that will be aging rapidly to be able to see potential benefits from rapamycin in the time frame of this study. And that was all factored into the power calculations, the demography of dogs in that age and weight range. I said that it may not be completely accurate to say that big dogs age more rapidly than small dogs, because there's a growing body of evidence, which we have some preliminary data in support of as well, that for brain aging and cognitive function, that might not be the case. That the rate of cognitive decline in big dogs looks, from a chronological sense, very, very similar to small dogs, even though the big dogs are dying at an earlier age. They don't seem to show accelerated cognitive decline, which is interesting. And I think there's a little bit of data, in people, although obviously people don't show the same diversity in body size that dogs do, so that's harder to see. It doesn't really seem to be the case that body size, accelerated aging due to increased body size, is reflected in brain aging. And the mechanisms there might turn out to be really interesting. So just an observation that I've noticed recently and I think might be important.
You're using once a week dosing. Explain to people, because we just mentioned it briefly and then said we'd come back to it now. We're going to sort of bifurcate mTOR into mTOR complex 1, mTOR complex 2, give people a sense of how those function and why it, on the one hand, is leading you to do what you're doing, me to do what I'm doing, and why in some ways it makes it a little bit interesting why the ITP found what it did with daily dosing. Let's tie all of that together, but first with an explanation of how mTOR works.
Sure. So mTOR, of course, is a protein. It's a kinase. We already talked about that. But it acts in a complex with other partner proteins. And so the mTOR protein acts in at least two. I think there's only two that we know of. Two different complexes called mTOR complex 1, or mTORC1, and mTOR complex 2, or mTORC2. And the difference between those complexes is that they have different partner proteins for mTOR. So there are a couple of things that are the same across both complexes, and then there are a set of partner proteins that are unique. And the two complexes do functionally different things in the cell. So mTOR complex 1, is largely thought of as the mTOR complex that is most responsive to nutrient levels. So when nutrient signals are low, that leads to lower mTOR complex 1 activity, and mTOR complex 1 downstream is known to regulate things like autophagy, mRNA translation, effects on metabolism, and mTOR complex 2 does different things. And I think we know a lot about what mTOR complex 1 does. We know much less about what mTOR complex 2 does, although people are studying that and learning more and more about what mTOR complex 2 does. From the perspective of aging biology, people have focused almost exclusively on mTOR complex 1. There's a little bit of data in C. elegans on mTOR complex 2 affecting lifespan. But outside of C. elegans, almost all of the data for rapamycin or mTOR as a regulator of aging is thought to be mediated by inhibition or reduced signaling through mTOR complex 1. So that's what people almost always think about when they think about effects of mTOR on aging. And rapamycin, as a drug, biochemically, is a specific inhibitor of mTOR complex 1. So the way rapamycin works is it's a small molecule that binds to another protein called FKBP12 or FPR1 in yeast. And once rapamycin binds to FKBP12, that complex of rapamycin with FKBP12 goes to mTOR complex 1, and you could think of it as sort of just messing it up, breaks it apart. So it inhibits mTOR complex 1 when rapamycin is bind to FKBP12. So biochemically, rapamycin is an extremely clean drug, and that as far as I know, and I haven't really seen any good data otherwise, there's no direct inhibitory effect of rapamycin on anything other than mTOR complex 1. What people have observed is that chronic long-term inhibition of mTOR complex 1 can have feedback effects on mTOR complex 2. And it's kind of confusing because there's actually some data both directions, that chronic inhibition of mTOR complex 1 can lead to activation of mTOR complex 2 in some context. Mostly, I think the data supports the idea that chronic inhibition of mTOR complex 1 with rapamycin can lead to inhibition of mTOR complex 2 in the long term. And that's definitely true in mice at higher doses of rapamycin. At lower doses of rapamycin, it's not completely clear to me how much effect on mTOR complex 2 there is. So the reason why that's interesting from the perspective of aging is I just said that almost all of the data for lifespan, at least, is that it's inhibition of mTOR complex 1 that leads to lifespan extension. Work from David Sabatini and Dudley Lamming when he was in David's lab led to the development of a model which I think is still the sort of preferred model. I will say up front, I think it's at least partly wrong, but it's the preferred model, which is that the side effects associated with rapamycin, particularly the metabolic side effects associated with rapamycin, are due to this chronic effect of inhibiting mTOR complex 2. So people will talk about rapamycin as if it induces something like diabetes, a pseudo-diabetes. And this is true in mice. There's evidence for it in humans as well, that chronic long-term treatment with rapamycin leads to glucose intolerance. So if you give a mouse who's been on rapamycin for a year a glucose tolerance test, they will not clear that glucose as rapidly as a mouse that never saw rapamycin. And the model is that that's due to the chronic effects of rapamycin on mTOR complex 2. Most of the evidence in support of that model comes from genetic experiments with mTOR complex 2 deficient mice. So I have yet to see a really clean experiment showing that's what accounts for the rapamycin effects on glucose tolerance. I think it's a reasonable model.
In other words, that evidence comes from creating genetic mice where you manipulate mTORC1 and mTORC2 rather than experiments where you give the mice rapamycin. I didn't ask Rich Miller this question because I'm pretty sure the answer is they didn't do it. But in all of the ITPs where the animals are getting rapamycin every single day, did they see impaired glucose tolerance despite longer life?
My recollection is they did not look, but there have been other studies, I think mostly in the C57 Black 6J mouse strain. So that's a different strain than the ITP, right? We don't need to get into it, but it's a different genetic background. But in the C57 background, you do see the same changes in glucose tolerance test at I think at the 42 part per million for sure rapamycin dose, so the higher ITP dose in older mice. So I think it's a real effect. I think you see that effect with rapamycin. And like I said, there's evidence in organ transplant patients for impaired glucose homeostasis as well. So I think it's a real effect. There's a couple of things that my intuition is it probably is due to mTORC2. I don't have any reason to doubt that. I just don't think it's been shown cleanly that that's the mechanism. Where I differ a little bit, certainly from Dudley, I'm not sure what David's view on this is right now. Where I differ from Dudley's interpretation is that I am less convinced that these effects that we see for glucose homeostasis are bad, right? I think there's at least as much likelihood that what this really reflects is an underlying change in metabolism that might actually account for part of the beneficial effects of rapamycin, where they shift away from primarily relying on glucose as the preferred carbon source and switch over to fat metabolism and maybe even ketogenesis to some extent. And when in that context, so it's a different physiological metabolic state. In that context, when you challenge them with a non-physiological amount of glucose, they don't respond the same way. So I don't know that it's actually a defect in glucose homeostasis. I think it may reflect the test that's done, and in some ways it's an artifact of that test that you get a different response, which is in the context of diabetes would be interpreted as a bad response. It might just reflect a different underlying physiological state. And I haven't seen anybody really try to address that. And what makes me believe that might be the case is we and others have seen that rapamycin treatment has pretty profound effects on fat mobilization, fat metabolism, adipogenesis, and at higher doses, ketogenesis. And so it would not surprise me at all if that metabolic adaptation accounts for some of the beneficial effects of rapamycin, and is also leading to this apparent aberrant response to a glucose tolerance test.
Yeah, it's interesting. When I've spoken with one other physician who uses rapamycin, although he uses it very liberally in many of his patients. I do not. I think his patients are coming in much older and much more metabolically deranged. And the results that he's seeing in an uncontrolled manner, meaning you simply have no idea what the performance effect of rapamycin is. So when you give it to somebody who's expecting to get better, they may go and change many other behaviors.
Of course.
But he's shared with me some of his data, and it's quite profound, right? So, triglycerides falling from, unhealthy levels of 200 milligrams per deciliter to 70 milligrams per deciliter. And actually they're seeing the opposite, right? They're seeing improved glucose homeostasis. Again, these are people starting who are pre-diabetic and in some cases diabetic. And I think your point's a fair one about oral glucose tolerance tests are very unnatural. And you can see a physiologic insulin resistance when you do them on people who are either calorie restricted or carbohydrate restricted, because that initial form of muscle insulin resistance is actually a protective element there. So all of that said, you've decided to go with once a week rather than daily, despite all of the other animal models that have shown great success with daily dosing. Is that a hedge?
So there's a couple. I don't know if I would define it as a hedge. I mean, I think that so the rationale there is both based on the human data, which again is limited, right? But we've talked about the daily versus weekly dosing for immune function. And again, we've also talked about why I think that readouts of immune function are probably telling us about the underlying inflammatory state, which I think is a big part of what rapamycin is doing. So that is suggestive that weekly dosing is at least as good as daily dosing. And it's also suggestive that weekly dosing has fewer side effects. And because this is a challenge with human clinical trials, as we've already talked about, it's also something you have to be, absolutely aware of when you're talking about doing a clinical trial in companion dogs, right? These are people's pets. There is an extremely, rightly so, an extremely low tolerance for significant side effects when we're talking about people's pets, right? I love my dog, and I would be, devastated if I hurt anybody else's dog in this clinical trial. So you want to do everything you can to reduce the likelihood of side effects. And there's reason to believe that once weekly dosing is likely to have fewer side effects. So, and there's also the pragmatic aspect of, we're asking owners to give this medication to their dog in the context of a clinical trial. We expect that there will be better compliance and fewer mistakes with once a week dosing versus daily dosing or 3 times a week.
So let's pivot a bit from Rapa to Taurin-2. You've recently, you and I have shared a couple of emails on this topic. Tell people a little bit about what that is and why you're excited.
Right. So Taurin-2 is a different version of an mTOR inhibitor. So we just talked about mTOR complex 1 and mTOR complex 2 and how rapamycin, at least biochemically, is a specific inhibitor of mTOR complex 1. Taurin-2 is a what's called a catalytic inhibitor or an ATP competitive inhibitor of mTOR, which at least in theory...
Versus what we call allosteric.
Allosteric inhibitor, which is rapamycin, meaning it interacts not through the catalytic site. Yes. At least in theory, Taurin-2 and Taurin-1 and other catalytic inhibitors will equally inhibit both mTOR complex 1 and mTOR complex 2. And for reasons that I still am not sure about, as far as I know, nobody has tested Taurin-2, Taurin-1, other catalytic inhibitors for effects on aging in mice. Why
seems like an obvious... This seems like something that needs to be submitted to ITP tomorrow, right? Or at least for the next cycle.
Yeah. I don't know. I don't know why it hasn't been done, to be honest with you. And maybe it has, and I just haven't seen the data. That certainly is possible. But I don't know of any data, not just for lifespan, but for, other functional measures of aging. I don't know of any data. So I don't know that I would say I can tell you why I think there's additional reason to test it beyond, sort of the rationale that seems obvious. But I don't know that I would say I'm excited about TORN2. It seems like an obvious gap in knowledge and would be actually a nice way to test the question we were talking about previously of TORC1 versus TORC2, good, bad, right? All of that stuff. It seems like an important set of experiments to do. And as far as I know, nobody's done it. So part of the additional reason why I think it's an interesting set of experiments to do is, in addition to studying aging, my lab also works on mitochondrial dysfunction and mitochondrial disease. And we have worked for many years in a mouse model of a childhood mitochondrial disease called Leigh syndrome. So this mouse is defective in complex 1 of the electron transport chain of the mitochondria, and it is very short-lived. It lives about 55, 60 days, and it develops many of the same molecular phenotypes and neurological phenotypes as kids who have Leigh syndrome, this childhood mitochondrial disease.
And these children typically live how long?
It's variable onset, but it's anywhere from infants to 8, 9 years old. Typically, kids with Leigh syndrome don't make it to be teenagers. It's a horrible, horrible disorder. So we found out many years ago that rapamycin could roughly double or triple the survival of these mice and basically prevent the neurodegeneration and brain lesions that are thought to limit lifespan in both the mice and the kids with Leigh syndrome.
And presumably, Matt, that's because when you knock out complex 1, you're destroying oxidative phosphorylation, and presumably the neurons are going to be the most sensitive to that.
Yeah.
Is that the thinking?
It's an interesting question. We don't really know. I mean, so I'll tell you the sort of current thinking in the field. So first thing is to recognize is this particular component of complex 1 is an accessory stabilizing factor. So the mice are not 100% deficient in complex 1. They have a low level of complex 1. I think you'd probably be dead if you didn't have any complex 1. And the same thing's true in the patients. So it's a deficiency in complex 1. And you're right. So one idea, there are actually several reasons why being deficient in complex 1 could be a problem. One could be you just can't generate enough ATP, and neurons or a subset of neurons are particularly sensitive, right? Another could be that you're generating high levels of reactive oxygen species. We know subsets of neurons are especially sensitive to that, right? And you could come up, there's also an inflammatory component to this disease where we see a lot of neuroinflammation in the brain regions where the lesions occur. And we don't quite understand what's causing that inflammation. So there are multiple ways that this could be causing, the symptoms of the disease. An interesting body of work from Vamsi Mutha's lab and Isha Jain, who was in his lab and now has her own lab, shows that hypoxia can also rescue these mice. And hypoxia actually rescues these mice to a greater extent than rapamycin. So that at least is consistent with an oxidative stress model, right? So one idea would be that when you're deficient in complex 1, those neurons are not using as much oxygen because they've switched over to non-oxidative glycolytic metabolism and fermentation. So you have higher oxygen levels in the brain. That leads to higher oxidative damage. When you reduce oxygen through hypoxia, you've suppressed that.
By the way, have you ever tried the experiment where you give them excessive amounts of lactate? Which neurons like lactate, and if you gave them lactate, in theory, you would also come up with a way to bypass the ETC. I mean, it would be an interesting control or way to test that hypothesis.
We've never tried that. So what I can tell you is they have higher levels of lactate in their blood. That's common in mitochondrial disease because they switch over to fermentation. But that doesn't mean that your experiment wouldn't work. It's just an observation. And rapamycin suppresses that high level of lactate, interestingly, as well as the accumulation of all the glycolytic intermediates upstream of lactate. So anyways, oxidative stress there's at least some reason to believe that oxidative stress is important. Another phenotype that these mice get is a dramatic loss of fat. So they are extremely lean. and rapamycin suppresses that. So we think that we know there's something going on with fat mobilization, adipogenesis, when we treat with rapamycin that spares those mice from presumably using up all their fat, right? Presumably they're trying to burn the fat in some way, and that's why they become so lean. So that's another observation. So how do we get to mTOR2 and taurin2? So we did a phosphoproteomic study with Judith Villen, who's at the University of Washington in genome sciences, to try to just take a sort of a global picture and ask, what is the effect of rapamycin on the proteome and the phosphoproteome in the knockout mice compared to wild type, and then with rapamycin treatment. There was a lot of interesting stuff in there. This work is published. It was published in Nature Metabolism, I don't know, several months ago. So if people are interested, they can look at that paper. There's a lot of interesting stuff in that proteomic data set, but one of the striking things that we saw was that mTOR2 components were at the protein level decreased, which actually fits with the idea that high-dose rapamycin chronically leads to inhibition of mTOR2. And associated with that was an inhibition of protein kinase C, which is another kinase that's regulated by mTOR complex 2. So that led us to hypothesize that, and protein kinase C is known to regulate some aspects of inflammation. So that led us to hypothesize that maybe some of the effects of rapamycin, at least in this mouse model, are through protein kinase C and mTORC2, as opposed to what we had assumed was all mTORC1 related effects of rapamycin. So we tested a few drugs that are known inhibitors of protein kinase C, and they rescued part of the lifespan of the mitochondrial disease mice. So they weren't as good as rapamycin, but they did give significant increases in survival and delayed some of the neurological symptoms that the mice experience. So that is consistent with the idea that this inhibition of mTORC2, inhibition of protein kinase C is part of the effect of rapamycin. So now we've gone back and we've tested taurin2 in this mitochondrial disease model. Seems to work, as well as rapamycin, which is interesting. No negative side effects that we can see from inhibiting TORC2 in that context. And then we're also working in another mouse model of a severe metabolic disease. And I think I'm not going to talk about it because this is a collaboration and it's not published yet. And so I don't want to give away, what the initial observation was really the observation of our collaborators. But let me just say, in another childhood metabolic disease, which is on the surface completely unrelated to complex 1 of the mitochondria, we see dramatic rescue from rapamycin and taurin2. So this makes me wonder, first of all, I've thought for a long time that mitochondrial disease might be a good model for normal aging in some respects. We know that, we talked about mitochondrial dysfunction as one of the hallmarks of aging. So severe mitochondrial dysfunction, I would not argue as accelerated aging, but I think interventions that are effective in a model of severe mitochondrial disease might also be effective in the context of normative aging. Everything we've seen so far is consistent with that. And it makes me wonder if taurin2 or other catalytic inhibitors of mTOR might be as effective as rapamycin in the context of aging, and maybe even more effective in the context of some age-related indications. So to me, it just seems like a gaping hole in the literature that really needs to be explored, and we'll learn from doing that sort of exploration. The other point that's interesting to make is RTB101, the drug we talked about previously in the Restore Bio phase 3 clinical trial, is a catalytic inhibitor of mTOR as well as other kinases. So it would fall, at least biochemically, into the taurin2 class as opposed to the rapamycin class.
How is taurin2 discovered or synthesized? Was it synthesized directly to be a catalytic inhibitor? Was it discovered and modified?
David Sabatini would be the person to ask. I should know the answer to that. My recollection, so rapamycin is interesting, right? It was found on Rapa Nui, made by bacteria. I think taurin2 came out of a more traditional sort of chemical screening as a mTOR inhibitor and then was modified to be a more potent catalytic mTOR inhibitor. But I honestly don't know that literature.
Does it already have an IND? Is there already a molecule that's in a pipeline, an FDA pipeline?
That's a good question. I have looked a little bit, and I don't know of anybody who's developing Taurin-2 or Taurin-1, which is another catalytic inhibitor, for FDA approval. And I've wondered about this, and honestly, I just haven't had the bandwidth to really dig into it. Is it because people tried and there were side effects? I don't know. But I don't know of anybody who's actively developing the taurins, at least, for FDA approval. RTB101, again, we talked about that's being developed or has attempted to be developed for FDA approval. There are other dual kinase inhibitors that are used clinically that hit mTOR in addition to other, like a PI3 kinase, a different class of kinase. So there are molecules that have similar types of activity, but I don't know of anybody who's really trying hard to develop the more specific mTOR catalytic inhibitors. And I'm not sure why.
Let's change gears for a second and talk about NAD, NR, NMN, all these things. I've had David Sinclair on the podcast a couple of times. He's very eloquently explained what sirtuins are, how they work, why they require NAD. So for folks who want to get up to speed on that, you can do so in great depth. Do you want to give the 30-second answer as to why sirtuins matter and why they need NAD?
Sure, but I would start by saying that I'm not sure that sirtuins are the only or most important reason why NAD is important. Right?
Sure.
So sirtuins are a class of NAD-dependent, mostly deacetylases. They also can do some other activities. But basically, one way to think about it is that sirtuins take acetyl groups off of other proteins. That's their activity, and that requires NAD, and it actually consumes NAD. So NAD is a cofactor for many metabolic reactions where it gets converted between NAD, which is the oxidized form of the coenzyme, and NADH, which is the reduced form. Many different metabolic reactions use NAD in that way.
Including the electron transport chain.
Including the electron transport chain, and glycolysis, and fermentation, yes. Sirtuins are fundamentally different in that they use up NAD, right? And so NAD is required for their activity. NADH, the reduced form of NAD, is actually an inhibitor of sirtuins. So the NAD to NADH ratio can be used as a proxy of likely sirtuin activity. So sirtuins are important in the aging field. This really goes back to my work as a graduate student in yeast when I was a grad student with Lenny Guarenti, when we first showed that you could overexpress the yeast sirtuin, which is called sir2. That's where sirtuin comes from. So the yeast protein is called sir2. If you overexpress sir2, you increase lifespan in yeast. And since then, other people have shown that activation or overexpression of sirtuins in worms or flies or mice can have interesting effects on aging.
You and David must have overlapped, right? You guys must have both been in Lenny's lab at the same time.
David and I overlapped in Lenny's lab, yeah. So he was a postdoc when I was a grad student. And I got to give David and I have had our scientific disagreements over the years, but I got to give David a ton of credit. As a postdoc, he mentored me in important ways, and I think actually guided me to the project looking at sir2, which is what I just talked about when we overexpressed sir2. So David was a very important early influence on my scientific career. And the Guarenti lab at that time, was full of really smart, I'm sure it's still full of really smart people, but it was just a really great environment.
It was a powerhouse.
Yeah, with lots of really, really fantastic scientists. So that was the first, and it was really Lenny's lab that established sirtuins as important in aging in multiple model systems. So in mice, I think, David might disagree with this a little bit, but I think if you're being honest, right, the evidence that sirtuins are potent regulators of lifespan in mice is mixed. It's not strong. There are a couple of studies out of probably, a dozen that have been published, and there's probably 24 that are unpublished where people saw no effects on lifespan from manipulator or activating sirtuins. There are a couple of studies that show, in one case, a brain-specific activation of one of the sirtuins called SIRT1 could slightly extend lifespan, and another that overexpression of a different sirtuin, SIRT6, could slightly extend lifespan, I think only in males. but nowhere near the reproducibility or magnitude of effect of other things, including rapamycin. So the data on sirtuins is broad, but the absolute effects on lifespan, at least, are, in my personal view, unconvincing. Like, it hasn't been broadly replicated like rapamycin has, and they're not big. What we do see with sirtuins is abundant evidence that metabolic markers of health can be improved by activating sirtuins. And in a few other disease-specific models, pretty good evidence, heart disease in particular, some evidence for cognitive function as well, improvements in age-related outcomes. So there's a lot of smoke there, but I think you know, there's a lot of confusion in the field about the relative strength of data for different interventions. And at least in my view, you know, there's really no comparison between the effects you get from inhibiting mTOR and the effects, at least so far, that people have reported from activating sirtuins. mTOR is head and shoulders above sirtuins when it comes to magnitude of effect.
Yeah, I think it would be impossible to dispute that. I don't think there could be any dispute of that. What's interesting is if I were to tally up the number of questions I get per month about NR and NMN versus rapalogs, the ratio is the exact opposite to the magnitude. So if the effect size of rapamycin and the importance of mTOR is 10x that of sirtuins, it's flipped in the number of questions I get about it, and just the pop culture awareness of that. So let's put the marketing of that aside and talk about the chemistry of it for a moment.
Sure. So I think right. So sirtuins are NAD dependent enzymes, right? So they need NAD to do their action. And we've already talked about, in general, the model is that turning up sirtuins is a good thing, right? That you're going to get, if you're going to get benefits in the context of aging, that's going to happen from activating sirtuins. Again, that's probably a pretty massive oversimplification, because there are 7 sirtuins, right? And they do different things in different tissues. But that's kind of where the field has gotten stuck, right? The idea is that activating sirtuins is good. And so if you accept that, and NAD is an activator of sirtuins, then more NAD is good. And there's good evidence that NAD homeostasis becomes impaired with aging. That the ratio of NAD to NADH, the oxidized to reduced form of NAD, in many tissues at least, shifts towards more NADH and less NAD, right? And so that with age. And so the prediction would be that you would have declining sirtuin activity due to that metabolic shift. And I will also note, because I think this is important, that in mitochondrial disease, you see the same shift. It's just much more pronounced. You see a shift towards NADH and less NAD. And that's exactly what you see when mitochondria are less functional, because the cells will switch over to glycolysis and fermentation, right? Fermentation to lactate. And the whole reason why we ferment to lactate is to restore NAD levels, right? Fermentation to lactate takes NADH and turns it back into NAD. So this probably reflects an underlying metabolic defect, which could be mitochondrial in origin, that leads to this shift towards the reduced form of NAD with age. So those two observations, less NAD, right, bad, sirtuins good. The prediction is that if we could boost NAD, that would be good, because that would then restore sirtuin activity and have effects on aging. And so this led to the development and popularization of these molecules called NAD precursors or NAD boosters, the two of which get talked about the most are nicotinamide riboside, NR, that was kind of the first to gain popularity, and then nicotinamide mononucleotide, NMN. Both of those are precursors of NAD that within cells can be converted into NAD. And so, you know, there's a large body of literature in a variety of model organisms showing that treatment with NR or NMN sometimes leads to benefits that are associated with healthy aging. And in one study, lifespan extension in mice. I say sometimes because there's also a large body of literature that doesn't reproduce those results.
Including the ITP.
Including the ITP, that's right.
Which is, I think, has to be considered the gold standard for at least mice data.
I think that's true. Although, as we talked about before, it's a different genetic background than C57 Black 6, right?
And
So
I would argue it's a much
publication-
better genetic background.
I think you can make that argument, and there are good reasons to believe that argument. Nonetheless, I think it's important to note, right, that could be why it worked in one context and didn't work in another context. And we've struggled with this as well in my lab. So, it's been reported in this mitochondrial disease mouse by a collaborator of ours who I trust their data, right? That NMN could increase lifespan in that mouse model. We've tried multiple times with both NR and NMN in that mouse model and been unable to get these effects. So I think these drugs are tricky from a biological efficacy perspective. There's something we don't understand about delivery or uptake that...
Do you think they're temperature stable?
Probably. Well, I mean, I don't know. I'm sure there are people who know the answer to that.
I've read conflicting things, right? I've read that, and I need to go back to the sources on it, but I've read that at least through the lens in which they're provided as supplements, the likelihood that by the time that thing arrives at your door, it still has the biologic activity that it would have had in a refrigerated manner is low. Now, I don't know that the companies that sell them recommend refrigerating them, but they might not recommend refrigerating them because then it would imply that they're being shipped in an unrefrigerated manner, which sort of nullifies the whole benefit. But
right.
I don't know if you've looked at any of that.
We haven't. So definitely in our mouse studies, we are careful to keep the food in the refrigerator until we put it in the mouse cage. I suspect that that there certainly might be some truth to the idea that the biological activity goes off over time at room temperature. But I think that reflects a bigger problem with the NAD precursor field, which is that there's a lot of controversy even among the two camps. So, I mean, it's sort of funny, right? Because there's an NR camp of researchers who really, think NR is the tool that we should use. And then there's an NMN camp, and they both, say that the other camp, that their molecule doesn't work, right? Because it's not biologically available or, all sorts of reasons, right? So there's a lot of lack of clarity around biological availability and efficacy with these molecules in the preclinical literature, right? Where, in theory, people should be able to exactly reproduce the way that other people do the work and get the same results, right? There are lots of reasons why scientific results don't get replicated. It's my impression that in the NAD precursor field, that's a bigger problem than in some other areas. And I don't know the reasons for that, but all I can say is we've experienced that in my lab as well. So I've tried to stay on the fence here because I think there's a ton of smoke, right? There's a ton of smoke with sirtuins. There's a ton of smoke with NAD precursors that they can, if you do the experiment the right way, have positive effects that look a lot like what we would expect for something that's impacting the aging process. And as I said, I mean, it's funny because, people who are in the field, I think sometimes think of me as this anti-sirtuin guy, which is absolutely not the truth. I'm the guy who first showed that you could overexpress a sirtuin and increase lifespan. If anybody's going to be pro-sirtuin, it's me. I think the problem is that I've seen a lot of data that people have struggled to reproduce, right? And I just honestly don't know how to interpret that. Whereas with rapamycin, it works for everybody, right? It's robust and everybody gets the same result over and over and over again. So I'm less enthusiastic, I would say, about sirtuins and NAD precursors as opposed to some other interventions, right, in the field. But I think there's a lot of data that suggests that these molecules and that sirtuins are important for aging. I think what we haven't done yet is figured out how to tweak the system in exactly the right way to get robust and reproducible experimental results that I personally would feel comfortable moving forward with clinically.
And it might be that the answer is you have to hit this system with two prongs. You have to provide more of the precursor and you have to activate the sirtuin in the way that resveratrol attempted to do but wasn't doing. Right. So maybe the answer is it's both. Again, that's literally just.
Sure, that's a possibility. The other thing that I find weird about the NAD precursor literature and the limited work that's been done clinically is often, I mean, in principle, it should be trivial to determine whether or not you have boosted NAD levels, right? If you treat somebody with an NAD precursor, we know how to measure NAD. That's not hard. Okay, so we know what the biomarker is, at least that far in this case. And oftentimes that's not done. So if you're treating somebody with NR or NMN and you're not increasing NAD levels in the blood or in your target tissue, that should tell you something important, I would think.
Well, and the other question is increasing it in the blood sufficient?
That's a different question, but it is an important question. I agree. That's why I said target tissue. And we can't biopsy certain tissues, but we can biopsy some tissues. Yeah.
No, it's super messy. Look, I get asked about it at least once a week by patients, and I usually point them to something I've written on the subject matter. But in the end, I say, look, I will say I think it's very safe. I really don't see a downside other than to your pocketbook of taking NR or NMN. I think they check the first box of any intervention, which is the downside sufficiently low? And I think the answer is yes. I'm just having a hard time seeing upside. So
yeah, and I'll tell you honestly, I would love to test NR or NMN or both in dogs for exactly that reason, right? Because there is essentially no risk, and we could actually find out, does it work? 3 years from now, 5 years from now, I could tell you, do NAD precursors slow aging, at least in pet dogs? And I think if I saw NR slow aging, increase lifespan, and or improve multiple functional measures of aging in dogs, I'd be much more bullish on taking NR myself. Wouldn't prove it's going to work in people, but it gets you part way there, and a pretty big part of the way there. And I would put that on the short list of things I would like to test. The fact is nobody's going to do the definitive clinical trial in people because they don't have to, because they can sell that stuff to people now, right? They aren't required to do the clinical trial to show that it works.
Yep. Matt, you probably don't remember this, but there was one night, 4 or 5 years ago.
Are you making comments about my cognitive decline with aging?
No. I just don't think you'd remember some random night of us having dinner in New York, but it was about 4 years ago.
Is this with you, Shin?
Yes. Okay, wow. You do have the cognitive function. So the three of us were having dinner at my favorite, not my favorite, but a decent Persian place on the Upper East Side. And I don't know if I said so at the time, but I might have told you after. It was after that dinner that I decided I got to do a podcast, because the three of us had such an enjoyable... She's at Einstein, isn't she?
She was, yeah. She's actually moved to Columbia. So now she's running a reproductive aging center at Columbia now.
Apropos with our discussion today.
Right.
But we just had such an amazing discussion, which really means me asking the two of you guys nonstop questions. And I remember thinking after that, God damn, why didn't I record this dinner? Why didn't I have my phone sitting on the table to record it? And it was literally that moment that made me realize, like, this happens the same time. Every time I go out with Sabatini, I have the same feeling. Every time I go out with so-and-so, I have the same feeling. I got to just do this podcast thing. So for anybody listening to this who is appreciative of the podcast, they owe you personally a great debt of gratitude for always providing.
Shin. I got to say, I'm sure it was you, Shin, who made most of the really insightful comments at that dinner.
I think it was both of you guys, so. but it was, it is always such an awesome time to be able to sit down with you. I think as the listener appreciates here, the breadth of topics within the space of longevity that you can cover is broad. So you're one of the few people who can go very wide and very deep. And I think today's discussion demonstrated that. So thank you very much, Matt. Really, as always, enjoyed this discussion.
Sure. Yeah. Anytime. I enjoy the discussion as much as you do, I think. So it's been a lot of fun.
All right. And best of luck with the triad study. I know a lot of people are probably more interested in that than any of the human stuff, because the dog owners I know care far more about what rapamycin can do for their dogs than they care about what it can do for them. So
absolutely.
Hopefully we'll have those results by the next time we speak. Thank you for listening to this week's episode of The Drive. If you're interested in diving deeper into any topics we discuss, we've created a membership program that allows us to bring you more in-depth exclusive content without relying on paid ads. It's our goal to ensure members get back much more than the price of the subscription. Now, to that end, membership benefits include a bunch of things. 1, totally kick-ass comprehensive podcast show notes that detail every topic, paper, person, thing we discuss on each episode. The word on the street is nobody's show notes rival these. Monthly AMA episodes or Ask Me Anything episodes, hearing these episodes completely. access to our private podcast feed that allows you to hear everything without having to listen to spiels like this, the Qualies, which are a super short podcast that we release every Tuesday through Friday, highlighting the best questions, topics, and tactics discussed on previous episodes of The Drive. This is a great way to catch up on previous episodes without having to go back and necessarily listen to everyone. Steep discounts on products that I believe in, but for which I'm not getting paid to endorse, and a whole bunch of other benefits that we continue to trickle in as time goes on. If you want to learn more and access these member-only benefits, you can head over to peterattiamd.com/subscribe. You can find me on Twitter, Instagram, and Facebook, all with the ID Peter Attia MD. You can also leave us a review on Apple Podcasts or whatever podcast player you listen on. This podcast is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient relationship is formed. The use of this information and the materials linked to this podcast is at the user's own risk. The content on this podcast is not intended to be a substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Finally, I take conflicts of interest very seriously. For all of my disclosures and the companies I invest in or advise, please visit peterattiamd.com/about, where I keep an up-to-date and active list of such companies.